Grr, arg. Welcome to statistical reasoning and other things to fear. Hey, welcome. I guess you've probably been missing me on these fun science notes as we now step into notes number 6, Statistical Reasoning, Part 1. And that first realm of things that people sometimes fear, that math and using your quantitative reasoning skills and what you learn about statistics as a way to answer questions and back it up based upon data, which is going to be massively important for the scientific method. So, sit back, get comfortable, relax. It's probably going to be a long one. As I begin my normal fade, bloop, 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 down to the bottom, and we start going with the scientific method. Okay. What's going on here? Ooh, technical difficulties to begin with. Sorry about that. There we go. So, as usual, I kind of like to start with some videos that give you a first-level introduction to stuff, and these ones are just on the idea of statistics and on numeracy, and then we'll dig deeper into the material.
Hi, I'm Adrienne Hill, and this is Crash Course Statistics. Welcome to a world of probabilities, paradoxes, and p-values. There will be games, and thought experiments, and coin flipping. A lot of coin flipping. Statisticians love to talk about coin flipping. By the time we finish the course, you'll know why we use statistics and how, and what questions you ought to be asking when you run across statistics in the world, which is all the time. Statistics can help you make a guess whether or not you're going to be accepted to Harvard. Marketers use them to sell us gold lame pants. Netflix uses stats to predict what show we might want to watch next. You use statistics when you look at the weather forecast and decide what to wear, dress or jeans. Policymakers use them to decide whether or not to invest in more early childhood education, whether or not to spend more on mental health services. Statistics is all about making sense of data and figuring out how to put that information to use. Today, we're going to answer the question, what is statistics? The legend says that during a late 1920s English tea at Cambridge, a woman claimed that a cup of tea with milk added last tasted different than the tea where the milk was added first. The brilliant minds of the day immediately began to think of ways to test her claim. They organized 8 cups of tea in all sorts of patterns to see if she really could tell the difference between the milk first and the tea first cups. But even after they had seen her guesses, how could they really decide? Because she'd get about half the cups right just by randomly guessing either milk first or tea first, and even if she really could tell the difference, it's completely possible that she would miss a cup or two. So how could you tell if this woman was actually a tea savant? What's the line between lucky tea guesser and tea super taster? As fate would have it, future super statistician and part-time potato scientist Ronald A. Fisher was in attendance. During his lifetime, Fisher began work that set the stage for a large portion of statistics, which is the focus of this series. These statistics can help us make decisions in uncertain situations, tea taste tests and beyond. Fisher's insights into experimental design helped turn statistics into its own scientific discipline. And although Fisher didn't publish results of the tea test, the story has it the woman sorted all the teacups correctly. Just in case you were curious. At this point, it's worth mentioning that there are 2 related but separate meanings of the word statistics. We can refer to the field of statistics, which is the study and practice of collecting and analyzing data, and we can talk about statistics as in facts about or summaries of data. To answer the question, what is statistics, we should first ask the question, what can statistics do? Let's say you wake up at your desk after a long evening studying for finals with a cheeseburger wrapper stuck to your face. And you wonder, why do I eat this stuff? Is fast food controlling my life? But then you tell yourself, no, it's just super convenient. But you're worried. You're thinking about how great it is that McDonald's serves breakfast all day right now. But maybe that's normal, right? I mean, finals are this week, so you Google the question fast food consumption, and you find the results of a fast food survey. The first thing you might do is start asking questions that interest you. For example, you could ask, why do people eat fast food? Do people eat more fast food on the weekend than on weekdays? Does eating fast food stress me out? Now that we have some interesting questions, we need to ask ourselves an even more important one. Can questions like these be answered by statistics? Like I mentioned earlier, statistics are tools for us to use, but they can't do all the heavy lifting. To answer the question about why people eat fast food, you can ask them to fill out a questionnaire. But you can't know whether their answers truly represent what they're thinking. Maybe they answer dishonestly because they don't want to admit that they scarf McDonald's because they're too tired to cook dinner, or because they're ashamed to admit they think Del Taco is delicious, or because none of the given answers represented their reasons, or they may not really know why they eat fast food. Armed with the results of the survey, you could tell that the most common reason that people reported eating fast food was convenience, or that the average number of meals they eat out in a week is 5. But you're not truly measuring why people eat so much fast food. You're measuring what we call a proxy, something that is related to what we want to measure, but isn't exactly what we want to measure. To answer whether people eat more fast food on the weekends, or whether eating it more than twice a week increases stress, we'd not only need to know how much people are eating fast food, which our questionnaire asked, but also which days they eat it. And we'd need an additional measure of stress. You can use statistics to give a good answer about whether you're going through the drive-thru more on the weekend, but even the question of whether eating fast food is associated with higher levels of stress is hard to answer directly. What is stress, and how can we measure it? And are people eating fast food because they're stressed, or does eating all those calories make them stressed? It's often the case that some of the most interesting questions are the ones that can't be answered by statistics, like why people eat fast food. Instead, we find questions that we can answer, like whether people who eat fast food often work more than 80 hours a week. The tools we use to answer these questions are statistics plural, and there are two main types, descriptive and inferential. Descriptive statistics describe what the data show. Descriptive statistics usually include things like where the middle of the data is, what statisticians call measures of central tendency, and measures of how spread out the data are. They take huge amounts of information that may not make much intuitive sense to us and compress and summarize them to hopefully give us more useful information. Let's go to the thought bubble. You've been working for 2 years in the local waffle factory. Day in and day out, you create the golden browniest, tastiest frozen waffles ever created. The holes are perfectly spaced, screaming for syrup. And now you want a raise. You deserve a raise. No one can make a waffle as well as you can. But how much do you ask for? An extra $1,000? An extra $5,000? You know you're valuable, but have no idea what other waffle makers get paid. So you dig around online and find there's an entire subreddit devoted to waffle makers. And someone, username Waffle Leaks, has posted a spreadsheet of waffle makers' salaries. Now, with a quick glance at this huge list of numbers, you can see whether the woman who works at a similar job at the rival frozen waffle company makes more than you. You can see how much more you're making than the new guy, who's just now learning to mix batter. But you still don't know much about the paychecks of your waffle company as a whole, or the industry, because it turns out there are thousands of waffle makers out there, and all you see is a list with data points, not patterns that can help you learn more about how much you might be able to convince the boss to pay you. Here is where descriptive statistics come in. You could calculate the average salary at your company, as well as how spread out everyone's salaries are around that average. You'd be able to see whether the CEO's paychecks are relatively close to the entry-level batter makers, or incredibly far away, and how your salary compares to both of their salaries. You could calculate the average salary of everyone in the industry with your job title and see the high and low end of that pay. And then, armed with those descriptive statistics, you could confidently walk into the waffle boss's office and demand to be paid for your talents. Thanks, Thought Bubble. While descriptive statistics can be great, they only tell us the basics. Inferential statistics allows us to make inferences. Clever namers, those statisticians. Inferential statistics allow us to make conclusions that extend beyond the data we have in hand. Imagine you have a candy barrel full of saltwater taffy. Some pink, some white, some yellow. If you wanted to know how many of each color you have, you could count them, one by one by one. That'd give you a set of descriptive statistics. But who has time for all that candy counting? Or you could grab a giant handful of taffy and count just those you've pulled out. which would be using descriptive statistics. If your candy was, in fact, mixed pretty evenly throughout the barrel and you got a big enough handful, you could use inferential statistics on that sample to estimate the content of the entire taffy stash. We ask inferential statistics to do all sorts of much more complicated work for us. Inferential statistics lets us test an idea or hypothesis, like answering whether people in the US under the age of 30 eat more fast food than people over 30. We don't survey every person to answer that question. Let's say someone tells you that their new brain vitamin, SmartyVite, improves your IQ. Do you rush out and buy it? What if they told you that the average IQ increase for Group A, 20 people who took SmartyVite for a month, was 2 IQ points, and the average IQ increase for Group B, 20 people who took nothing, was 1 IQ point? How about now? Still not sure? It's a pretty small difference, right? Inferential statistics give you the ability to test how likely it is that the two populations we sampled actually have different IQ increases. However, it's up to you as an individual to decide whether that's convincing or not. And don't be alarmed if the bar you set isn't the same in every situation. It's entirely okay to have different standards for the questions, does my cat like Fancy Feast more than Meow Mix, versus does this drug cure lung cancer? It might take more evidence to convince you to take a new, supposedly cancer-curing drug than to switch cat food brands. It should take more evidence to convince you to take a new, supposedly cancer-curing drug than to switch cat food brands. With inferential tests, there will always be some degree of uncertainty, since it can only tell you how likely something is or is not. Your job is to take that information and use it to make a decision despite that uncertainty. If statistics were a superhero, its bat call would be uncertainty, and its tagline would be, when you don't know for sure, but doing nothing isn't an option. Statistics are tools. Statistics help us make sense of the vast amount of information in the world. Just like our eyes and ears filter out unnecessary stimuli just to give us the best, most useful stuff, statistics help us filter the loads of data that come at us every day. Descriptive statistics make the data we get more digestible, even though we lose information about individual data points. Inferential statistics can help us make decisions about data when there's uncertainty, like whether SmartyVite will actually increase your IQ. But statistics can't do all the work. They're here to help us reason, not to reason for us. They can help us see through uncertainty, but they don't get rid of that uncertainty. To push our tool analogy a step further, statistics like chainsaws are pretty useless, even dangerous, without understanding how they work. We need to know how to use them and how not to use them. As we'll see in later episodes, statistics done poorly can lead us to some pretty silly conclusions. And chainsawing done poorly leads to about 36,000 injuries in the US each year, 81% of which are lacerations. Did you know that almost no one dies because of chainsaw injuries? Once in a while, but it's very rare. 95% of the people who are hurt by chainsaws are male. This does not necessarily tell us that males are significantly worse chainsawers. Statistics can help us plan a vacation to Bali in December. They can help us optimize our chances of winning our fantasy football league. They can help us budget our meal card at college. Statistics can help us decide whether that additional insurance the guy at Best Buy is trying to sell us on our new blender is actually worth it. Statistics can also help us decide whether or not to go ahead with an invasive heart surgery. Statistics can help NGOs optimize the amount of food aid they send to refugee camps. They can help policymakers decide if they should spend more or less money on helping students pay back their school loans, and can help you decide how much money you should be comfortable borrowing for college in the first place. There's a lot statistics can help us with, but some things statistics can't do. Thinking statistically means knowing the difference. So when your brother says he used statistics to prove that your mom loves him more, you can rest easy, knowing the only question he answered is whether she gives him slightly more ice cream each night. And you've got data suggesting she gives you extra sprinkles. Thanks for watching. I'll see you next time. Crash Course Statistics is filmed in the Chad and Stacy Immigholt studio in Indianapolis, Indiana, and it's made with the help of...
Okay. So that's a longer video, but it's a very good introduction that goes over kind of a general overview of everything we're going to do in this lecture for stuff. But before I go in, I wanted to go through playing this one more video that they introduced in this series, and it's mathematical thinking in relation to numbers and being careful what does that mean with quantities.
Hi, I'm Adrienne Hill. This is Crash Course Statistics. In the last video, we talked about why we care about statistics, how we use statistics, and statistics is math. So we thought we'd take a detour today from the traditional curriculum to talk about how to think about numbers, really, really big numbers, really, really small numbers, and how to make sense of them. We're also going to talk about mathematical thinking and fighter jets. Chances are, if you're watching this channel, and certainly if you're commenting below, you're literate. You understand language and how to use it. But are you equally comfortable with numbers? And I'm not talking here about being able to calculate square roots in your head, or instantly tell whether or not 17,321 is prime or not. And it is. I looked it up. Numeracy is about being able to wrap your head around what it means when politicians talk about a $1.5 trillion budget hole. It's about getting a handle on how much you should really lose sleep over the chance of an Ebola outbreak, and how to compare that risk to the chance of being killed by a terrorist, or a snake bite, or dying from an opioid overdose. And it's about what those comparisons might tell us about the time and resources we spend trying to address those problems. Mathematical thinking is about seeing the world in a different way, which means sometimes seeing beyond our intuition or gut feeling, because it turns out most of our guts are good at digesting food and pretty bad at math. Infants, less than a year old, can discern between 3 objects. I am much more advanced than an infant and can pretty easily comprehend the difference in 1 and 100, even the difference between 100 and 1,000, or maybe even 10,000. For most of us, once numbers get really big, we lose our ability to have any intuitive sense of them. The distinction between 1,000,000 and 1,000,000,000 and 1,000,000,000,000 is really hard to visualize. There are 100 trillion bacteria in each of our bodies in non-mathematical guts. 100 trillion. There are an estimated 10 quintillion insects that are alive right now, and an estimated 300 sextillion stars in the universe. So how do you even begin to think about those big numbers and what they mean? Let's go to the thought bubble. Take a minute to visualize the difference between 1 and 100, and 1,000, and 100,000, and 1,000,000. That's a lot of dots, a whole lot of dots. There are other good ways to try to make sense of big numbers. You can try to put the number in context. The US debt is in the neighborhood of $20 trillion. About 323 million people live in the US. So the debt owed for each person is about $62,500. You can also turn a big number into a unit of measurement that you're more comfortable with. The Kola super deep borehole, which is the deepest artificial point on Earth, is 40,230 feet deep. I have no idea how deep that is until you tell me that it's about 7.5 miles down, and I can start to picture it. You can also have reference points for big numbers ready to go. There are about 100,000 words in a 400-page novel. About 46,000 people show up to Dodgers games in Los Angeles. I can roughly visualize that. 1,000,000 people taking to the streets to protest might be easier to think of as 21 Dodger stadiums worth of people, or 14.5 crowds for a Real Madrid match. Time can help us go even bigger. 1,000,000 seconds is a little less than 12 days. But what about 1,000,000,000 seconds? Do you think you are 1,000,000,000 seconds old? Well, are you older than 32? It takes 32 years for 1,000,000,000 seconds to pass. And what about 1,000,000,000,000 seconds? Think you or I will be alive after 1,000,000,000,000 seconds passes? Sorry to break it to you, but no. We will not. Even if you are destined to be the Guinness Book of World Records oldest woman, there is a 100% chance, barring massive medical breakthroughs, that you will be dead. It takes 32,000 years for 1,000,000,000 seconds to tick by. Thanks, Thought Bubble. A quick note about scientific notation. Scientific notation can be really helpful for calculating with big numbers, but not necessarily helpful for understanding them. Without context, exponents can be non-intuitive, if that's a word, in their own way. 10 to the 39th and 10 to the 32nd sound like they might be close, but 10 to the 39th is 10 million times larger than 10 to the 32nd. We're not going to run the dots on that one. There are about 7.6 billion people on Earth. 7.6 billion. Understanding the sheer number of people out there in the world can help us make sense of the commonness of coincidences or improbable events. Some statisticians call it the law of truly large numbers. The idea here is that with a large enough group or sample, unlikely things are completely likely to happen. Consider this example from statistician David Hand. On September 6, 2009, the Bulgarian lottery randomly selected as the winning numbers 4, 15, 23, 24, 35, and 42. And then, 4 days later, on September 10th, the Bulgarian lottery randomly selected new winning numbers. 4, 15, 23, 24, 35, and 42. Exactly the same numbers. People freaked out. Bulgaria's sports minister ordered an investigation. Was it fraud? Something else? Hand says, calm down. It's just coincidence. He lays out the math to prove it, but part of the argument here is the law of truly large numbers. If you consider the number of lotto drawings every week around the world over years and years, it would be amazing, he wrote, if draws did not occasionally repeat. Speaking of those incredibly unlikely things, we need to talk about the flip side of incredibly big numbers, the incredibly small numbers that can also be hard to comprehend. Take the likelihood of winning a Mega Millions jackpot in the US. Right now it's about 1 in 302.6 million. The probability that you'd win the jackpot is 0.00000003305. Let's put the teeny tiny chance of that happening in some perspective. 302.6 million is the number of seconds in more than 9.5 years. So to borrow here from a very funny post by Tim Urban on Wait But Why, that's like knowing that a hedgehog will sneeze once in the next 9.5 years and betting on the exact second during those 9.5 years that the hedgehog will need a tissue. And I'm going with May 2nd, 2:23 and 33 seconds p.m. 2021. Our inability to judge small numbers does more than just cause us to misjudge our chances of winning the lottery. It causes us to worry about the wrong things, to fear the wrong things. Take your chance of dying from Ebola. If you live in the US, the chance that you'll be killed by Ebola in any given year is pretty close to your chance of winning the Mega Millions lottery, 1 in 309.6 million. It is among the very, very least likely ways anybody living in the US will die in a year. Though you are, by some accounts, less likely to be killed by a terrorist attack in the US committed by a refugee. In a 2016 study, researchers calculated that as a 1 in 3.64 billion chance in the US in a given year. And you're far more likely to die in dozens of other ways. There's a 1 in 6 million chance someone living in the US will be killed in a given year by a bee sting. A 1 in 708,000 chance they'll die falling from a ladder. A 1 in 538 chance they'll die in a given year from cancer. And not a big cause of death, but did you know that people die in sand holes that they or their friends have dug out at the beach? They crawl in, looking for a little time in a sand hole, and whoosh, the hole suddenly collapses and they're buried. Stay out of sand holes. I'm gonna stop because it's stressing me out. The point here is that it's worth taking the time to think through small numbers because they can help you figure out what's actually worth worrying about and what isn't, what you might want to act on, and what you might want society to take more and less seriously. My personal takeaway is that I'd be way better off spending more time exercising and less time looking around obsessively for poisonous snakes because the annual odds of dying from a snake bite in the US are only about 1 in 34 million, but the odds of dying from heart disease in any given year are 1 in 534. Thinking mathematically isn't just about understanding numbers better. It's about asking important questions about the world around us and letting numbers illuminate those questions. One of my favorite examples of mathematical thinking is the story of Abraham Wald and the missing bullet holes. Hat tip here to mathematician Jordan Ellenberg for highlighting the story. Let's go to the news desk. World War II, Manhattan. A group of statisticians and mathematicians are hard at work trying to protect American fighter pilots. Their task, trying to figure out how best to armor planes without making them too heavy, so our heroes can outrun and outwit the enemy. In an effort to figure out how best to protect our planes, the statisticians pore over data of the planes that return from fighting, looking at where they took damage, where the bullet holes were. That data showed there were more bullet holes in the fuselage and fuel system, and not as many in the engines. So how do we save our American heroes? The exceptional statistician Abraham Wald studied the data and came back with advice that surprised everyone: to put the armor where the bullet holes weren't, over the engines. Wald realized the bullet holes should have been more evenly distributed over the planes. If fewer planes were returning with holes in the engines, that meant those planes weren't returning home. Wald had the exceptional realization the data wasn't a random sample of all planes. It only represented the planes that returned. He suggested the military add armor to the engines. American lives were saved. Not all mathematical thinking is going to help you save lives, but it will help you make better decisions. Mathematical thinking can help you see past coincidence. It can help you judge risks. It can help you see the broader relationships in the world. Thinking mathematically gives us something to go on other than our guts and their trillions of bacteria. Thanks for watching. I'll see you again next time. Crash Course Statistics is filmed in the chat.
So once again, a longer video, but both of these videos together combine to give good flavor for what we're working on, this importance, especially this mathematical thinking when putting stuff into context, because we're going to be working through some statistics and numbers where we'll start with no context interpreting it, but once you throw that into a context and you start using these tools, you can start making different decisions, and you have to take things into context. The importance of this. So, longer videos in the beginning, but well worth it when it comes to everything else we're about to go through. Now, statistics itself, that whole thing that may scare some people away, but really it's just the fact, when we're doing science and we've hit that experimental section and we've got to start gathering data, so doing that measurements on our dependent variable after making changes to independent. And we're going to have a lot of data values, i.e. building up our population of data that we've actually gathered. And if it was only a few values, we could quickly make some decisions, but what do we do when it comes out of scope and we can't see patterns really from all these separate numbers? What can we do? And that's where statistics comes into play. It's a measuring of data, interpreting that data to prove or disprove a point. That's it. That's what we're going with. That becomes part of our argument, that we're backing it up with these kind of empirical evidence, these other measurements, and then drawing conclusions from it when they've gotten to be such a large amount of data, and getting it down to something that we can then start interpreting and digging deeper. So, statisticians and scientists collect and work with large amounts of numbers and measurements. Then they calculate how the numbers relate to each other and how they affect each other. Kind of like how we're talking about that causal relationship we've gone through before, and where we think we have a cause and effect relationship. We've identified our independent variables. We set up experimental conditions, and we try to gather evidence to try to establish causality, establish that causal relationship. And here in science, is a key part of that establishment is going to be this gathering of this measurable empirical data, and then looking and analyzing that data and using some form of math to do that. In a lot of cases, it's statistics. So if you know the basic statistics, what the numbers tell you, and you learn how to collect or obtain accurate, reliable, and good numbers related to facts, you can arrive at good conclusions, and you're well in your way of developing a meaningful statistics-based analysis and reasoning. And that's why we need to go through this for this course. If you're going to be evaluating someone else's work or setting something up that's from the scientific method and within a science culture, you've got to build your skills related around statistics to be able to understand what they're saying, something you may not be used to, or how you say something back to them that they can then understand, and how it ties back to everything else within the scientific method. So again, statistics itself is just another branch of mathematics, dealing with data, collecting, organizing, analyzing, interpreting, and presenting. In addition to being the name of the field, it also refers to the numbers itself and the data you're gathering. So these tools and the relationships you have, the specific statistics tools you use and the data that you find and gather. Now, again, that also expands us just as a science of learning from data. That once we gather this and we have these independent numbers, it doesn't become just something randomly on a piece of paper or in some document. We start looking at it using different tools to gather and get new information out of it and learning, well, okay, what can this tell us? And then based upon that, how can we start making some informed decision? How can we start using our deductive, inductive, and abductive reasoning skills combined with quantitative reasoning to come to a conclusion? And it's a crucial process behind a lot of the discoveries and decisions and everything that's made, and when testing things like your predictions. And so this still expands upon this. We see the patterns. It's also looking at things like frequencies, how often you see something, distributions, how is it spread out in the data that we're looking at. Is there randomness? Is there cause and effect relationships of the data points of the study? So between the mapping of changing an independent variable to the measurements that you got in your dependent variable. It's also used to determine things like the measure of the center of it, so what's most common within the data, the spread being how far it branches out, and the frequency of how often you see stuff. And based upon those kind of your tools, you can then put it into context of the situation you're looking at and make some decisions and see what's going on and build stuff up from there. Now, another important part, hey, don't. I mean it, just don't. Just take a breath. Don't get scared. I know there's some math symbols up there. Some esoteric, math, magician-y stuff that gets really confusing and trigger stuff. But don't. Those are just symbols that are there that we may not understand now, but as you get deeper into the culture, you can build upon it. And if you're going to do anything with statistics, you got to have something related around statistical literacy. Understanding the basic language and tools of statistics, what is in there, the meaning, understanding of the symbols, and recognizing how to interpret them and how to use them, and how does that relate then back to the data and values that you've actually measured. So really, they may look confusing, but as you dig deeper, you'd be like, oh, okay, that's a part of science again. Why math is a language of being concise, and how you get one symbol, and okay, that means summing something up, and the sigma, that means standard deviation, or it means something else, and a clear way to represent that. And so we need to understand those and kind of build upon it. We won't go too deep in this course. We'll get a few of them. But it's important when you're relating this that you have to start building that literacy of just even those basic symbols and growing from there. So being statistically literate allows you to access and use data more effectively for informed decision-making, including being able to evaluate number-based claims in the media. When they say even terms, not even just symbols, but things like the median value was this, or the mean, or the average, or the standard deviation, and you pick up then like, well, what does that mean when they say those terms in context with some number? And understanding what someone else is saying as decision versus you making a claim and trying to communicate that clearly to someone else that has a background in stats. So recognizing words that imply much but assert very little. So on their own, something like median may not mean a lot just if you had no background with it, but when you understand from statistical background literacy that there's a lot of power and a lot of background behind words like median and the other symbols. And so you want to grow from there and kind of get used to that and kind of dip your toe into it, learn a few terms. Maybe some will stick, maybe some won't, but the more you do that, the more it becomes a natural habit ingrained, and it becomes something a little bit easier over the time, over the years, and anything else. So, and then build upon that as statistical reasoning. We've talked a lot about reasoning before this in this course, that making an argument. And for going logical reasoning, then sequential steps that you go through to get to an actual argument that also allows someone to backtrack on those steps and understand that reasoning. And then we went down to quantitative reasoning, where you're taking something mathematical, a context, and a problem you're working with, and you're trying to come to some kind of solution. And so here, statistical reasoning is just kind of narrowing it down, that quantitative reasoning is specifically done through the use of statistics and those tools and those terms to come to your conclusion. So when we have a massive amount of data, we are specifically, from the mathematical sense, using a lot of statistical tools to make those decisions as part of that quantitative reasoning step. So statistical reasoning is the way people reason with statistical ideas and make sense of statistical information. It may involve connecting one concept to another, i.e. like idea of center, or like measures of center, measures of spread, or may combine ideas about data and chance, so probability, and like understanding where all of this comes from and how to interpret these results and making those connections. So it's going to be like knowing, like, how do I know what tools are there? How do I understand they work? And how do I make connections between them, almost like they're individual premises? And you're doing some kind of deductive or inductive reasoning and saying, well, okay, well, this is what the median tells me, and this is what the standard deviation tells me, or this is what the range tells me, and how do those combine then together within the context that I can get some more inference out of it and come to a conclusion and back up my argument based upon the actual data I found, not my personal beliefs in this case. So statistics and science literacy expands your science literacy and your ability to interpret material in the media and science publications. So we've already gone through some basic kind of idea of like scientific literacy and the importance of certain words. Now this is just expanding it, getting to that stats. And when you see it used in other areas, you can may not be perfect in the beginning, but you can understand where that's coming from, and then you know where to grow and learn and do more from it. It also expands our vocabulary. So if we're going back to our science as a culture, this now means when we're interacting within the culture and other people, we have a lot more vocabulary to start communicating with them. We can pick up more within conversations and hopefully be able to react and learn. And we also have new ways of talking about things in a quantified way, instead of a vague kind of way, giving some kind of quantities of percentiles or numbers or terms that tie it back, that imply that behind the statements I'm making, there is data, there is numbers, there's quantities to work with. Now, for example, if we go kind of the top-down view of looking at kind of the end result of studies and some kind of statements, we want to look at some of these and see, well, what are they really saying within it, and where does that quantified nature come from it? And now you have to remember, when we're looking at these next topics, this is results coming from the end of the scientific method, so that communication phase. And so when you see these statements, these aren't endpoints with nothing else from them. You have to remember to connect back to that scientific reasoning and realize, okay, well, this is the last step, so I should be able to trace all the steps back to the very beginning and see their entire argument. And I presume that's there. I know that we got to this point. I read conclusion, therefore there must be previous steps to it, and I should be able to back those up. And you can see this here where these are actual studies, and I've given the references to them. You can try looking up if you want. I haven't, but these are starting points. So modern science is often based upon statements of things like statistical significance and probability. Now, I've highlighted those two terms because, again, that's going to expand upon our vocabulary. We're not going to go too deep into them in these notes, but the next following up notes, when we go into Statistical Reasoning Part 2, we'll talk about, well, why are those so important? But I just wanted to highlight them here now, as those are terms that if you hear them in the media or in other sources, you should realize, okay, those hold a whole lot more weight to them when it comes to science as a culture. So, this first study. It's an actual one. So studies have shown that the probability of developing lung cancer is almost 20 times greater in cigarette smokers compared to non-smokers. Now, we may nowadays have a presumption, like, oh yeah, that's just what we presume, that's what I've heard, but you have to, like, this study's back from 2004, and it's a different era. That's, at this point in time, 16 years ago. And so you're like, well, what does that actually mean? And so in this terms, you have to realize, well, they're backing stuff up. They didn't just say the terms that people who smoke have a better chance of getting lung cancer compared to non-smokers, which kind of implies quantity, but doesn't really say anything about how much. Whereas here instead they say things that are almost 20 times. So that means for every one non-smoker, and if you're a smoker, you have possibly have 20 times the chance of getting cancer as compared to them. Doesn't mean you will for sure, but you have a better chance. And well, if that's really big, it was only a 2 times chance. Well, 20, it's a lot larger. Other ones, there is a significant likelihood of a catastrophic meteor impact on the Earth sometime in the next 200,000 years. By Jeebus! What are we going to do? A meteor's coming. We've only got 200,000 years. Oh wait, this paper's back from 2005, so we've got less. We're under 200,000 years. Well, we don't know yet. We have to see where this is coming from and the likelihood, and this is probably based upon their own data, but they're still talking about quantities and kind of giving you a range of when it could happen and react. Another one. It's a good one, especially if you're siblings. And you're the older sibling and you have younger siblings. Firstborn male children exhibit IQ test scores that are 2.8 points higher than second-born males, a difference that is significant at the 95% confidence level. So some of that probably could have just sounded like wah, 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 numbers don't care. Or it could sound like, whoo, science has proved that me as the older sibling is smarter than you as the younger sibling. So you might as well listen. Science says it, so it's true. Well, we have to dig down deeper into this, and there's more to it in understanding this is the end result and seeing what can we talk about this. But we've still more to see from here, like that stats and kind of quantitative and numerical and mathematical thinking working its way into these final statements. Things like IQ test scores. That's tests that give back a numerical value and a way of like quantifying someone's intelligence. And even though IQ scores and stuff like that probably could be under suspect, who knows? It's just talking about the numbers and having to understand that. And here, things like 95 confidence level. Well, may not mean much to you, but for someone who has a background in stats, well, that becomes something that's very important for what's the probability of this happening beyond just pure chance of these two connections. And how can we start doing things with that? So, really, as we sit here, like, what are they saying? Like, why do scientists speak in terms that seem obscure? Like, if that didn't make any connection to you, it's probably more the fact that, well, if they're in that culture, statistics plays a key role in math as well as part of that language and how to communicate things. And so if you don't have a background on how to communicate that, you won't realize how important maybe those customs are when this relates to science. Because things like, well, if cigarette smoking causes lung cancer, why not simply say so? If we should immediately establish a colony on the moon to stay our existence from complete destruction, why not inform people so we can start doing this now? It's going to take a huge societal shift to get that to happen. But also, also at the same time, if older children are smarter than their younger siblings, why not just let them know? Even though some older siblings probably would revel in the fact of doing that on their own. Statistics, the reason that none of those latter statements accurately reflect the data, they don't show it here. Scientific data rarely leads to absolute conclusions, which some people don't seem to like, but that's just not life. That 100% this is only going to be that way. It's always that evolving based upon the evidence and what we know to this time and how it could be changed. And if it's backed up strong enough, we can believe in it from that data and that empirical evidence. And so these previous statements, not saying you get, it may not be what you expect. Cases here, not all smokers die from lung cancer. Some smokers decide to quit, thus reducing the risk, or some people who smoke maybe have other reasons for it, of unhealthy eating patterns at the same time, and alcohol abuse and other stress, and maybe it wasn't the smoking that caused the cancer or caused the actual death. So we can't always rule that 100% that if you smoke, this is going to happen, but we sure as hell can check on other reasons why. Some smokers, like here, may prematurely die from cardiovascular diseases or other than lung cancer, and some smokers may simply never contract any diseases and any other conditions. And so we need ways to deal with these cases when that may not always work perfectly. And like all data exhibits some kind of variability within it, and is the role of statistics to quantify this variability and allow scientists to make more accurate statements about their data. So even though there's these outliers in cases where you can't 100% say that this is the cause and effect and this is going to always happen, we can start saying, well, this is the likelihood of it. And if we find the likelihood's high enough, like this 90% chance of it happening, the 20 times over something else, then we can start making decisions that, well, what can we do is the best that may not catch everyone, but should do the majority or give us a better way to go in this uncertain craziness of the world. And giving some kind of quantified way of talking about that, like 95% confidence levels or p-values of some certain level. So, like another thing with statistics, a common misconception that statistics provides a measure of proof that something is true. But they don't actually do such a thing. It's not really about proof. Instead, statistics provides a measure of the probability of observing a certain result. Because proof, you have to remember back when we talked about that before, is either true or false. It's a dichotomy. It's one or the other. There's nothing in between. Whereas the statistics give you that probability of a spectrum of completely impossible to, yes, 100% certain, and some kind of scale between that. Like a test you got a score on 0 on, you're like, I'm not going to be happy, versus getting 100% versus getting 90% versus getting 70%, and how you feel in relation to getting that percentage on a test. This is the same thing as that probability. And then we can start making critical decisions based upon that. If we find something that's large enough, or what they would say is statistically significant enough, to say that's beyond just random chance, that the probability of this happening is like 90%, maybe we should go forwards with this. So other examples I can pull from, and these are older ones, but like ways to quantify and start making decisions and connect stuff together, and why we talk about stuff in probabilities and these sense, and not just this exact 100%, and not just jumping into saying that everyone in science, the science community, can't agree upon one thing. It's like, well, no, there's different studies and different backing of the data, and everyone's just having a conversation to come to an answer. And then there's going to be generally overall what is the largest probability and what's been accepted overall and reproduced and accepted by the community now, knowing that it could change in the future when new evidence comes into play. Like, we'd want to have this evolution. So here, back to the study. For example, the American Cancer Society has conducted several massive studies of cancer in an effort to make statements about the risk of the disease in the United States. So, Cancer Prevention Study 1 enrolled approximately 1 million people between the years 1959 and 1960. And they did another study later on called Cancer Prevention Study 2, which was taking larger, enrolling 1.2 million people in 1982, and using these both the study stuff. We'll be going deeper into these a little bit later in the next notes, but for right now this is just a top level. Both of these studies found much higher rates of lung cancer amongst cigarette smokers compared to non-smokers. However, not every individual in these studies who smoked contracted lung cancer. In fact, some non-smokers did contract lung cancer. So we got cases there where some people smoked for the cause, and the effect lung cancer, and they did get that, but then some didn't. And there were some cases where people got lung cancer, but they never smoked. That doesn't mean, okay, we should throw this out. There's nothing connecting these. Well, there's probably multiple reasons and more complex reasons what causes lung cancer, and multiple causes that could be coming from here. And just because we can't say that smoking is 100%, we should throw it out, is that if there's a likelihood it's one of the causes, we should react to that, and then maybe discover other causes that come from here. So now, instead of being a proof concept, these studies kind of show that the development of lung cancer is a probability-based event, not simply just a cause and effect relationship. So when we looked at cause and effect, it becomes more the probability of that chance of this cause leading to that effect and not showing that 100%. So maybe we back it up by there's an 80% chance of this happening. So it means with that cause of smoking, you have an 80% chance of getting lung cancer. So some people would, some people wouldn't, but probably a lot more people who do smoke would, and we should probably react in that case and make decisions based upon those kind of quantities. And so you'll see a lot more of that in science writing, and you'll see this probability. And so that's why statistics is important to understand from here, is understand, well, what do these probabilities actually say? How do we interpret that, and how do we communicate that, and not just passively step back and say, well, I don't need to know that, or that makes no sense, we'll throw it out, it's rubbish. Well, it's a different culture. It's got to understand from that side, and then also know when are the good and bad parts of it. When do stats get misused, and so forth. So more with stats, what we get a step from here in a communication within science and that culture is stepping away from vague statements and trying to make them a little bit more specific, tied to kind of quantified, probability-based events. So statistical techniques allow scientists to put numbers to this probability, moving from vague statements like, if you smoke cigarettes, you're more likely to develop lung cancer. It's very vague. You don't know how much, where, when. We get more specific statements, but that's backed by data, such as the probability of developing lung cancer is almost 20 times greater in cigarette smokers compared to non-smokers. So both are talking about similar cause and effect. Just one of them gives you more information and uses specific quantities within it to make decisions, and it's backed up by the data that's behind it, that we know that this is the last statement in overall experiment, that we should be able to go back, and there is that data that should be empirical, so we should be able to measure it using similar tools and hopefully come to similar conclusions and kind of challenge it and work our way back to understand the argument and maybe repeat it and add to that knowledge base or innovate off from there with what we're doing. So it's important that you understand the difference between these two statements and kind of take a chance to realize, well, why is the first one vague, not having quantities, versus the second one saying a similar thing but being more specific, and knowing that those numbers came out of statistics, came out as the end result of those tools, and gave those scientists more power in how they communicated and what makes it different from when they communicate within those terms. So all those little nuances. So statistics. Quantification of probability offered by statistics is a powerful tool used widely throughout science. As such, statistical methods are used extensively throughout the scientific process, from the design of the research question through data analysis and the final interpretation of that data. And we saw some of that before and have mentioned things like the correlation coefficient, like the example of R, is that sometimes to try to establish that association is that first step of proving causality, that you have some data and you can kind of generate that correlation coefficient to get some quantified way of talking about that association and what direction it goes in and how strong that is, and if you should continue with it or not. Or we go into the experimental procedure design and we realize that's where we're going to be gathering our data. And so when we're designing that, we have to understand how stats work to make sure that we're designing things properly to gather the right data and not introduce bias and unnecessary things that could weaken our overall argument. So it's everywhere. And then even down to the analysis, once we've gathered the actual data, we got to look at it, make interpretations of it, analyze it, add to our argument, and then come to some kind of final conclusion of accepting or rejecting the hypothesis and predictions that we've set up. So the specific methods vary widely between different fields, from psychology to chemistry to biology to computer science throughout. And so you have to understand within those fields, what is the important things, what are the tests, how are they used, but are the reasons that these tests and techniques are actually used is similar across it, as the backing it up or argument, that quantitative reasoning, being able to deal with these probability-based events. So, numbers, got to get to them, and let's start small. And just think, like, here, let's take some data. So assume that these are measurements that have come from something. We don't even know the units. We have no context of what they relate to. And with no context, what could you say about this small sample of data? And so our population, you could say here, of data, these 6 numbers. And, well, it's a small thing, so for relation numbers, we can start, like, we don't know what is small is good number, is the small number is good, or the large number is good, or is it bad, or vice versa. We don't know. We'll need a context for that, but we can kind of look and see what we're getting. Or, like, I don't know, take a few minutes to look and see what you see. But I kind of noticed, like, oh, look, 2s. Look, like we got 3 2s. Those are repeating. That's interesting. I see, like, the smallest number I see is 1 from there, and the largest number I see is 7. I don't know the context, but those are kind of patterns that I'm kind of seeing so far. So things like, okay, I have smallest 1, largest 7, 2 appears the most often from here, and then here I'm throwing an average. Most of kind of us have dealt with that. We'll go into it later on when we talk about mean, but it's, it's summing up all the numbers and dividing it by how many numbers you get, and the average of this is 3, which is that kind of measure of centralness of it in that kind of range. So, it's interesting. You can see some patterns, but we have no context from here. But with a small set of data, that's kind of easy to do. I can just look at it, and there's not a lot there. I don't have to spend a lot of time. I can quickly notice it just by looking. Other things we can do. So, I got new information out of that data. I have the term smallest, largest. That's new information. We found it from here. Things like appears the most. That's new information. Well, 2 appears the most is a new piece of information that pulled out of the data that maybe is important if we had some context to this, but right now we don't. Other things we could do, we're so used to this, graphing. We could take the data and we kind of measure and graph it out or check on things and see how visually it looks and kind of describes the data overall. In this case here, this is just like a little frequency or kind of histogram where you're counting, okay, well, for each number is 1, 2, 3, 4, 5, 6, 7 from right here. Because, the smallest is 1, the largest is 7, so we don't have anything from here. So we can kind of make a number line with all those on here. We can count how many times each number appears. So there's 1, 1, and 3 2s, and there's no 3s. There's 1 4 and 1 7 because visually. And we can see that average now, that yellow line I've kind of drawn in here. And the average is that centralated, where you can see, well, okay, it's kind of splitting the data a little bit. If we think from left to right, we now kind of have a left side and we kind of have a right side. So overall here. So, that left side, this right side. And like, well, this 3 here and this average is not one of the actual data, but it kind of splits it. It also doesn't split it evenly. You can see here, we're like, okay, well, there's 4 here, and there's 2 over here. But it does kind of show centrally, like, we have some here and here, we got these clusters, and kind of splits them apart. So there's something visual. Maybe we could get fancy and, get some fancy kind of, like, displaying of these graphics. Same frequency, but now here, when we have it for 2, you can still see it's all 3 2s, and, we got that 1, we got the 7. But here, then now we just used a tool. In this case, I used Excel to kind of generate this graph and kind of fit a line that curved overall, and allows us to visually see stuff. And this is something part of statistics, those tools that we get to draw stuff and infer from. We still have the original numbers. They're just up here. We looked at them some, but now here's a tool. Take it, graph it in a certain way, and we've generated some new information in a different way to see it that we can probably pick up on things. And we see like, oh, we still have that kind of splitting, but you're like, whoa, there's a lot of 2s here. Like, what's happening over here? There's a lot. That's a big, steep hill versus these little hills and mountains over here. Like, what's happening between these 2 sides, and what could we tell about it? Now, let's give some context you're used to. Your lifelong of having to do a lot of tests and getting used to that. So what if we say now that we were looking at this data and we have 1 2 4 7 2 2, but this data was based upon a test that was given. So a group of students right here, in total, like 1 2 3 4 5 6 students were in a class. They're given a test, and the test was out of 8 marks. And so each of these scores you're seeing is the score a student got on that test. And so now with that context, we can start looking at these numbers, and we start seeing things like, okay, well, if it's out of 8, Well, okay, and we get zero, so we have some context. Okay, low numbers are bad for scores because, that's like a zero. That's not good. You're always trying to go higher. So within a context of the exam, we now know higher numbers are better and lower numbers are worse in this context. It could be different in others, but we know that. So up here is better, down here is not so good, and overall here is how roughly the class did, but we know that there's these extreme outliers. But quickly looking, if we were to say something in this context and try to answer a question like, how did the class do? You're like, I'm not so sure how the class did. Maybe something's wrong with the teaching or something happened that day, because a lot of students got like a 2 out of 8. That's not a good score at all. And even if we are kind of splitting this from different sides of being a 3 is still not good. This 4 is like a 50%, and this is 100%, so below this is not good. But you can see now I can kind of quantify. I can start looking at the numbers and say, well, okay, it's below a 4, and that's a 50%, and this amount of students got below that. We can even start counting them. Well, 1, 2, 3, 4. For half the class got below 50%, and the other half got above. But of that 50% that's below, you're like, well, 1, 4, 5. Like it's just more from this. But see, we can start giving with these stats more quantified ways of just saying, well, the class didn't do good. We can start saying, well, how, and analyzing that. And we saw this more from pulling stuff out and viewing the data in different ways and using statistical tools like graphs like these to do that. And that's just a small amount of data and information. Let's change a different context. So same data, but that's ninja attacks. Or just something attacking you. Cowboys from here. Surprise pop quizzes from teachers. And so if we take it instead that, okay, well, it's the number of attacks or something that happened on a day of the week where 1 is Monday, 2 is Tuesdays, then Wednesdays and Thursdays and Fridays and so forth. And we're just counting up maybe over a 2 to 3 week period, how many things happen. Let's say here, we'll just say it's 1 week. So in 1 week, how many times there were attacks on different days. And if I was looking at this data for context, is, well, this time lower numbers are better because I'd kind of like to not be attacked at all. So those days where there were 0 are good, and those days where they're higher, it's not so good. And so now this time to interpret, it's kind of like an up-down in this case, and you're like, well, 2, this lot happens, so Tuesdays suck. Why? Because there's these 3 attacks versus, say, the next day on Wednesday where there's no attacks. Probably because you're recuperating from all those ninja fights on Tuesday. 3 ninja fights on Tuesday, Wednesday means healing, so you're not being attacked versus everything else happens, so forth. But you can just see it's the context of the numbers and being able to quantify it. And this is just a small amount of data of only being these 6 data points. And so we're able to do stuff by looking, but what if they're only... Okay, then. What can we start saying about this? What the heck's going on here? I got back to no context. Great, thanks. Thanks, teacher. No context and a large sample of measurements, as if this was like a ton of measurements coming out of an experiment. So these are all the measurements you've done on your dependent variable. And you want to say, well, analyze it. And you're like, I don't know. You guys can look at it. I don't know what's going on. All I can see is like the Matrix, Neo, red pill, blue pill kind of things. If you get the reference to the movies that I'm talking about at all, because those are old movies now. But more, the only pattern I can really quick and see is like there's all the numbers are only single digit. There's no double digit. It's the only thing I can quickly see because the way this is spaced out. But like I can't quickly see what's going on. Maybe the smallest is 0 out of this. I don't see any negatives, and I'm not too sure what the largest is. It's going to take me a while to work through this. And this is where having other tools like statistics and being able to plug in tools that we just dump in the data to it and then hit a button and it's going to generate stuff for us or make formulas in Excel, or knowing what tools to use that are built in as stats. Like, we need something else from this. We need to do more with it. And so maybe we could use some of those tools and tell it to find the smallest and largest. And we can just see, even if you manually did this, let's just assume I spent forever looking through this manually to figure out, and I finally got these numbers here at the end. I don't know which one's easier to stare at. Like, the stuff on the left that's just a big square of numbers, or the stuff on the stuff on the right that's a big square of numbers, on the left, which is kind of what you could say is your statistics. You pulled out information that was generated from this, that and is tied to it. This was generated using this data. Now we can look here to kind of give a feel for what's going on. And you're like, okay, this time smallest is 1 and the largest is not 7. Wow, checking my stats. Look at that. I'm going to embarrass myself right here. Look at that big, look at those 8s, and the largest here saying 7. Yeah, that's supposed to be 8. Either way, this is why it's good to have other people validate and check stuff. We also have things like here, appears the most is 2, the average is 3.76, and then say down here, which is still missing 8, unfortunately, but we say maybe the frequency count. So every time we saw 1, we give a little tick and we counted it up, and now we can quickly see, okay, well, 84, that means 2s appear the most, and we can maybe start giving a context and start building off of this. So this was just a small example of like when you get larger and larger massive amounts of information, you start needing to have visual ways to represent stuff, to see it and look at this stuff differently and gather some data. And sometimes these new numbers, like we see on the left, those are your statistics. That's what you're growing with. That's what you're starting to build with to generate new information and give some context to this wealth of what else you're seeing. And also things like this, graphs. So this is just that same data that we saw before, but now graphed on average and having a visual way to look at it. Whereas we started with this, and then, we got some of these numbers here on the left. Okay, that's a little bit easier to understand, give some context. Then we get this graph, and we're like, okay, I can kind of see what's going on if there's a frequency distribution, kind of on the frequency distribution, like a histogram, kind of counting frequency of stuff to this, so I get a better idea. So a lot of that, what I did, it was just to give you kind of a feel or context for what we're doing. And I got some other examples, but it was important to understand those tools to analyze and work with that data. So your statistical tools being the types tools, like things like mean is a tool, average, and those kind of things that hold weight to them, those are your tools. We need to build upon this. And like these tools give us ways to dig into that data and start pulling out new information, like how many things appear, certain things from there, and help us interpret large amounts of data and give us some context. So drawing graphs, using other tools, and then connecting those together using quantitative reasoning and combine that to a context to draw conclusions from that are logical steps. So what do we need to know? What tools to use and what information they provide us with, when to use those tools, the good and bad aspects of these tools, because not everything's perfect. You have to understand the flaws of what you're working with and using the information provided by the tools when making decisions and how we do that. So these notes are going to go through a lot more of the tools and giving you a working context to build from. And then future notes, other examples, are going to go through other problems of like, okay, well, here's a problem, here's the generated stats, and okay, what decision can you make based upon those? So these notes will be very important to go through and get a good foundation with to build up that statistical literacy and problem solving and knowing where to find your tools, new keywords to help you search for other videos, other material if you need that extra help. And so to begin with, we need to break down the actual overall tools and categories. There's a lot of the tools that are out there, but we start to know what families and different areas and how do they fall into each other. And so generally it falls into 2 groups or camps of types of methods. So we start overall the entire family of statistical methods, and that breaks down either into descriptive methods or inferential methods. And you saw that already from the video earlier on. And so like these notes are going to stick a lot with descriptive methods and probably delve into inferential methods in the future. But in descriptive methods, you have the whole category of different types of graphs you can use for the data and learning what those graphs are useful for and how to read them, how to set them up. You also have numerical summaries. So these are like that smallest or largest or average that take that data and bring it back generally to one number or a couple of groups of numbers that have a context behind them that then allow you to pull things from it. And the inferential methods give you confidence intervals, so that 95% confidence level, and significant tests, things like that, the t-tests, chi-square tests, your p-values and stuff from there. So before going on, as usual, always like to have a video. This one's a little bit shorter, but gives you another context and examples. And I'm always trying to bring in a bunch of examples, and I think it always does help to bring in different ways that other people talk.
There are two major branches of statistics: descriptive statistics and inferential statistics. Descriptive statistics is the organizing, summarizing, and displaying of data. So we would go out and collect information from a sample or population, then organize the information, then summarize the data, and then display the data, maybe in a chart like this. Inferential statistics is using a sample to make estimates or draw conclusions about a population. So we would collect information from a sample and then draw conclusions about the population that sample was from. Let's take a look at an example for the following statement. Descriptive statistics involves the statement, 83% of dental patients who had a female dentist felt their dentist cared for their emotional well-being during their procedure. It would also involve the statement, 61% of dental patients who had a male dentist felt their dentist cared for their emotional well-being during their procedure. Inferential statistics would involve making an inference that a female dentist is more likely to care for your emotional well-being during a dental procedure. Alright my friends, I have more videos right there for you. Till next time, I am out of here.
So, it's a good background. Now, beware, we're already about an hour and 15 minutes in, so if you haven't taken a break, gone and done something else, I suggest you do it now. Just pause the video. Think back on what's happened so far, take a break, get something to drink, relax some, and come back to this. Because we're on only slide 37 of 110 for these notes, so got a ways to go, so I do suggest taking a break at this point in time, pausing it, and coming back. I'll even fake pause. Okay, we're back. And I'll continue on with this. So again there, like those categories, remembering that descriptive statistics describe the data, so you'll get those graphs and the summary kind of numbers, and they give you a way of, instead of randomly looking at the data as a large scale, they kind of give you different visions, like filters from your eyes. Whereas inferential statistics studies samples of data, so whatever you're looking at, and then try to infer new things you can draw out of that actual information. So the descriptive statistics allow science to quickly sum up major attributes of a data set or population using measures such as the mean, median, mode, and standard deviation, and things like range and other stuff that we'll be going through here. And so that mean, median, mode, and standard deviation are those kind of summary descriptive statistics numbers, and then also using things like graphs and other stuff. And they're calculations you make to tell you, okay, what's happening with this data I'm looking at. And so a general sense of what's going on with the group you're looking at. And it also allows you then to take two different groups and gather these same kind of piece of information and compare them together. So instead of having two large groups of separate groups of measurements or numbers and individually comparing each number to number, it now gives you that chance of, okay, we'll compare the mean between the both of them, and the median, the mode, and the standard deviation combined with the mean, and how much does one grow versus the other, and there's a big enough change between these two groups, and what can we tell what's going on. Whereas inferential statistics are used to model patterns in data, making judgments about it, identifying relationships between variables in the data sets, and making inferences about the larger population based on a smaller sample. So even cases where we can't sample everything that happens, like talking to everyone in Mount Royal, maybe we can't. We'll just talk to a subset of them and hope that that's a proportionately right, that could then be extrapolated to talk about the larger population, and hope that we're not too far off within these actual levels. So again, the rest of these notes will concentrate now on descriptive statistics, and the next notes will maybe go a little bit into inferential statistics. So we've broken down like the normal statistical methods. We need to now break down descriptive statistics a little bit more. And we can generally kind of think about some of being either measures of central tendency or measures of dispersion. So most central tendency being that likelihood of one in the center, common values, versus dispersion being spread out. And then those are still their families or types of measurements. And we get down to specific ones like mean, median, and mode, and range, standard deviation, variance, interquartile range. These are specific tools. Those are the tools inside those actual boxes. And so mean will be a calculated one that sums it up and you get some data out from it. Now, these are just sticking to that numerical kind of quantities, and there's still the whole breakdown of category that's not shown here of different types of graphs that you could use. I am going to introduce one in these ones to help you visualize stuff a little bit better and being able to interpret that. But there are a lot of other ones you can start learning about and realize different tools to visually graph and describe the data combined with these individual methods and bring them all together to make some kind of conclusion or answer. So as usual, I want to go back. This is the original video series. It's probably another longer video, but I think it's a good first introduction if you want to summarize everything that we are about to go over and what's the importance of these measures of central tendency.
Hi, I'm Adrienne Hill, and welcome to Crash Course Statistics. In the last video, we tried to make sense of ginormous numbers and teeny tiny numbers. Today, we're going to talk about less showy numbers, the numbers stuck in the middle, the averages, the medians, the modes. They may not seem as mind-blowing or all that flashy, but turns out they're really, really important. Those middle numbers are often the ones that get all the press attention, get tossed back and forth in political debate. And they give us this little fun bit of trivia. What's the average or mean number of feet people have? It's not 2. Turns out the average number of feet people have is a little less than 2, because the average takes into account the small number of people out there with fewer than 2 feet. So if you have 2 feet, you have more than the average number of feet. And with that, let's get into measures of central tendency and why they're useful. If your boss asks you for a report on this quarter's sales numbers, but is rushing to a meeting and only has time to listen to one piece of information about that data, that piece of information you give her should probably be a measure of central tendency. The center of a bunch of data points is usually a good example or summary of the type of data we can expect from the group as a whole. One common measure of the middle is the mean. You've likely heard it called the average, though all of these measures are sometimes called averages. Some people call the mean the expectation of a set of data. The mean, or average, takes the sum of all the numbers in a data set and divides by the number of data points. So if 10 pregnant dogs give birth to 50 total puppies, the average litter size is 5 puppies. Each data point, in this case each litter of puppies, contributes equally to the calculation. Aww. Here's another example. Say you have $10 and your best friend has $20. The mean amount of cash you two have is $15. 10 plus 20 divided by 2. But saying that the mean is $15 doesn't mean you each can buy that $12 BFF necklace that you've been eyeing. You know, the one with half a heart that fits together? You personally only have $10 in your pocket. The average of a set of data points tells us something about the data as a whole, but it doesn't tell us about individual data points. The mean is good at measuring things that are relatively normally distributed. Normal means a distribution of data that has roughly the same amount of data on either side of the middle and has its most common values right around the middle of the data. Data that are distributed normally have a symmetrical bell shape that you've probably seen before. A distribution shows us how often each value occurs in our data set, which is known as their frequency. Imagine you're trying to impress your new college dorm mates by guessing how many times they've each seen Harry Potter and the Sorcerer's Stone. Your mom is in the entertainment industry and you overheard at her last dinner party that 18-year-olds on average had seen the movie 5 times each. That's a lot of Quidditch. So you should guess your new friends have seen the movie 5 times each, unless you can clearly see Slytherin tattoos. You won't be right each time, but it's your best guess. It might not be the best way to impress them though. It's really not a great party trick. Sometimes the mean is misleading. For instance, life expectancy in the Middle Ages. As we explored in Crash Course World History, there was an incredibly high rate of infant mortality in the days before modern medicine. But the people who made it to adulthood lived relatively long lives. Because of the high rate of infant and child mortality, the average life expectancy was about 30 years. But things weren't nearly as dire as all that. Not if you actually made it to 30. In the 13th century, a male who who lived to 30 was likely to make it to his 50s. To give unusually large or small values, also called outliers, less influence on our measure of where the center of our data is, we can use the median. Unlike the mean, the median doesn't use the value of every data point in its calculation. The median is the middle number if we lined up our data from smallest to largest. For example, if you have 2 cats, Jillian has 1 cat, and Eric has 3 cats, the median number of cats in your little cat-loving group would be 2. When we put the number of cats in order from the least to the most cats, 2 is in the middle. But what if there's no middle number? You invite Will to join your cat group. He has an impressive, or is it excessive, total of 14 cats. Now there are 4 cat owners. There is no one middle number. Both 2 and 3 are in the middle. In this case, there are differing opinions on how to calculate the median, but most often we take the mean of the 2 middle numbers. So our median would be 2.5 cats. Meow, meow, me. Let's go to the thought bubble. Imagine 10 artists have been working for years together to come up with a new, fresh way to tie macrame knots. The standard square knot just wasn't inspiring them the way it used to. And finally, they do. Voila, the abracadabra Doolittle knot. So these 10 artists go out to celebrate, and they go to a relatively modestly priced restaurant because macrame artists just don't make all that much money. Each of them pulls in about $20,000 a year. So the average, or mean income around the table is $20,000, and the median income is also $20,000. Now let's imagine that Elon Musk gets wind of this macrame milestone. Turns out he's a huge macrame fan himself. Beauty in design. He couldn't miss up a chance to celebrate, so he decides to show up at the restaurant. Musk's total annual compensation, including his salary and stock options, is reportedly in the neighborhood of $100 million. As soon as Musk walks in the door, the average income in the room skyrockets to a little over $9 million. But nobody else in the room is actually richer. Nobody feels any richer. The median income of the macrame artist and Musk is still $20,000 because most of our group is still making $20,000. And this isn't just the stuff of our make-believe macrame world. It happens in real life too. The average is distorted by outliers. Thanks, Thought Bubble. All right, now say there's a controversial book on Amazon called Pineapple Belongs on Pizza with 400 reviews, 200 5-star reviews, and 200 1-star reviews. The mean number of stars given was 3, but no one in our sample actually gave the book 3 stars, just like no one could actually have the median of 2.5 cats. In both of these situations, it can be useful to look at the mode. The word mode comes from the Latin word modus, which means manner, fashion, or style, and gives us the French expression a la mode, meaning fashionable. Just like the most popular and fashionable trends, the mode is the most popular value. But we don't mean popular like Despacito popular. When we refer to the mode of our data, we mean the value that appears most in our data set. For our Amazon reviews of Pineapple Belongs on Pizza, the modes are both 5 and 1, which gives us a better understanding of how people feel about the book. These reviews are called bimodal because there are 2 values that are most common. Bimodal data is an example of multimodal data, which has many values that are similarly common. Usually multimodal data results from 2 or more underlying groups all being measured together. In the case of our book, the 2 groups were the love it 5-star group and the 1-star group. Or for another example, if we made a graph of the times customers went to In-N-Out, we'd probably see 2 peaks because there's 2 groups of people, one around lunchtime and one around dinner time. The mode is useful here because it's an actual value that occurs in our data set, unlike the median and mean, which can give us numbers that wouldn't actually occur and don't describe our data very well. The mean time people come into In-N-Out may very well be 3:30 p.m., but that doesn't suggest you should expect an overflowing restaurant in the middle of the afternoon. You should be able to get your animal-style burger and fries without too much of a wait. The mode is most useful when you have a relatively large sample so that you have a large number of the popular values. One other benefit of the mode is that it can be used with data that isn't numeric. Like if I ask everyone their favorite color, I could have a mode of blue. There's no such thing as a mean or average favorite color. The relationship between the mean, median, and mode can tell us a lot about the distribution of the data. In a normal distribution that we mentioned earlier, they're all the same. We know that the middle value of the data, the median, is also the most common, the mode, and is the peak of the distribution. The fact that the median and mean are the same tells us the distribution is symmetric, that there's equal amount of data on either side of the median and equal amounts on either side of the mean. Statisticians say the normal distribution has zero skew, since the mean and median are the same. When the mean and median are different, a distribution is skewed, which is a way of saying that there are some unusually extreme values on one side of our distribution, either large or small in our data set. With a skewed distribution, the mode will be the highest point on the distribution, and the median will stay in the middle, but the mean will be pulled toward the unusual values. So if the mean is a lot higher than the median and mode, that tells you there's a value or values that are relatively large in your data set. And a mean that's a lot lower than your median and mode tells you there's a value or values that are relatively small in your data set. Let's go to the news desk. The average income of a U.S. family grew 4% between 2010 and 2013. Those average paychecks expanded from $84,000 to over $87,000. But not everyone is cheering. The median income fell 5% during those same years. Median family income dropped from $49,000 to just over $46,500. This really happened back in the years after the financial crisis. The mean income rose at the same time the median income fell. That's because families at the top of the income distribution were making more money and pushing the mean up, while many other families were making less. And even though unscrupulous politicians could accurately claim average incomes are rising and pat themselves on the back, it would be misleading. For most Americans during that stretch, incomes were flat or falling. This points to another really important point about statistics, a point we'll come back to time and time again in the series. Statistics can be simultaneously true and deceptive, and an important part of statistics is understanding which questions you're trying to answer and whether or not the information you have is answering those questions. Statistics can help us make decisions, but we've all got to use our common sense and a little skepticism. Thanks for watching. I'll see you next time. Crash Course Statistics is filmed in the Chad and Stacy Imigholt studio in Indiana.
So once again, that video series does an excellent job to sum up what I'm going to go through more examples. So I do suggest you maybe dig deeper into that course and other ones they provide. They do an excellent job. And good examples, and gives a nice beginning summary to give you a feel on some of the keywords that we're going to now go through a little bit more in depth. And so starting off, we'll get into that category of that measure of central tendency. So those extra tools that we're looking for. So when we're confronted by a large list of values, we can often ask the question, what is the typical value? What is an average value? So what are we kind of commonly seeing? It may not be perfect to represent everything that we're seeing, but it's a starting point by like, well, I see this most commonly, or this is kind of that kind of range, and then I can get a feel overall for that and combine it with some other stats. And so these are all asking for measures of central values. And measures of central tendency are used to describe what is normal for that set of data working with. And there's different tools that have their good and bad parts from it. So a measure of central tendency is a single value that attempts to describe a set of data by identifying that central position, what is normal. So based upon all of the data points that we calculated, you get one number back that kind of describes in different ways what is normal for that case and tied into it. Such measures of central tendency are sometimes called measures of central location, and they are classified as summary statistics. So falling under that descriptive statistics, they summarize up the data you're looking at. Like, hey, look at all these values, and this is what I'm seeing the most. And this is what's tied to. And what's going to be important here, this vocabulary and holding that weight, is that there are different kind of specific tools for central tendency, like mean, median, and mode. And they have different meaning behind it when you say that number. Like a mean of 4 versus a median of 4 versus a mode of 4. That's like your units. There's different meaning. Like all of it, you heard me say the word 444 or some other random word. And if you don't have any context or background with that, it doesn't hold much meaning. But in that science kind of statistical reasoning, statistical literacy, it's very important. They're all the central tendency of trying to talk about what is most normal, but different, how they're calculating, getting those normals is slightly different. And all three of them together can be used to tell other information like those skews. So under different conditions, some measures of tendency become more appropriate to use than others and give you more information. So here we're going to kind of use all three of these to combine stuff together. And here, this is just like a quick cheat sheet and kind of showing you some of this stuff of like the mean being the average, median is middle most value, mode is the most commonly seen. Don't worry, I'm not rushing through these like crazy. We're going to go through these individually. And you get things down below like the skews. And if we're seeing the data, and these are like kind of frequency charts you're working with of how often you see each value between a range that could be higher or lower, and then the clumps of, well, is it more clumping on one side versus the other side versus centrally, and what does that tell us? And you can kind of see here of how different values of how much larger or smaller the mean or mode or median are from each other. We may not be able to visually see these kind of like humps all the time, but based on how these numbers arrange, we can infer and feel and through those numbers know, okay, well, this is what's happening. And if there's more data on one side, say like higher scores versus in the bottom of lower scores, that can also tell us more, and we can make decisions from there. What's the norm for this data? So throughout all the rest of these notes, we're going to be building up an example and working with one specific one as we go through stats and keep coming back to it. And I always wanted to pick one that I thought we could, again, all relate to, which is test scores. Something you're used to and can kind of understand and relate to in your lives. So like we'll use the following data as example explaining each of the following stats tools. And the context is an exam has been given to a class of 40 students. Kind of like this class. So far we have 40, or maybe there's more or less. The test was out of 100 marks. So we know automatically from this is that the lowest possible score a student could get is 0. And in my class, I'm not one of those mean teachers where you get negative marks. And the highest you could possibly get is 100 because it's 100 marks and there's no bonuses or anything that. So we know if we made a number line from this that we'd have 0 up to 100. And I put some dashes in here for measurement every kind of 10 test scores. And so we know we have that range of what's the smallest to largest. So possible values for our actual data in this context. Other contexts will be different. Now, also, what is good and bad is different in different contexts, but we know in a test, you're like, let's say everyone's just trying to do their best, and so you want to get higher scores. Higher numbers mean you're doing better on that material as assessment, and that's why I've kind of got the faces here from the red to green and unhappy to happy from that spectrum, saying that lower spectrum, things like down this way, is lower scores and not so good. This is mediocre, middle, neutral to being really good. And that's the context here. Now, in a different context, like you remember that ninja example, is maybe something's different from that. And you got to realize, what is good for ranges? Is smaller numbers good or smaller numbers bad? And it depends on the context. And you have to have that in place first to make sense of the data tied to it. And it's part of your quantitative reasoning that we have a context to work with. So this is where we're at. Now here's the actual raw data score. So you can go through and manually calculate all this data, plug into other tools, and validate and see that hopefully I didn't make any other mistakes like the previous one, but this data I checked over multiple times. And so we have 40 students, and so we have 40 numbers here. So it's the individual measurements that we've actually gotten back, and this is the score that they got out of 100 marks. And you can see right now it's maybe a small amount of data, but it's hard to see patterns. If we just look straight at that data, it's hard to see what the heck is going on. And we're going to need some of those other stats tools to start having ways to describe and look and generate new information, get new understanding and new viewpoints on this data. If we want to figure out how is this class doing overall. So, okay, we've got these numbers. So one thing we could start doing is maybe doing another kind of like histogram or frequency distribution, a frequency kind of counting of this. And so I've done that here. And I've just decided, just so the graph looks a little bit nicer, is that when I've done the counting, I kind of made bins, and I was counting, well, how many times did someone get 0, to how many times did someone get between 1 to 10, versus 11 to 20, and 21 to 30, kind of counted it up. And then from there, kind of map this out. And you can see already that if we go back to the data, we've just got that numbers, and this is the same thing, same numbers, but we're using those statistical tools and the descriptive statistics being these graphics and these kind of summaries here of just counting up with the bins is that first level to see something different. And so you can see in the bottom, I've included that little happy whee passing to look, oh, what's happening? Down here at the bottom, kind of scale matching up to it. And already we can probably get a feel, even just from this graph, how this class is doing. There's a large number of stuff over here that if these are good scores and these aren't, like there's this whole thing of like, whoa, like even here halfway through the test, which we would know would be 50%, you're like, okay, that's not the best. But you look, you already have that tool that we couldn't see that. Like that was harder to see from this previous slide, that we have all these numbers and I couldn't see that. But here we go. Oh, okay, I can start making decisions. I can back up the data. I could use this chart and use the count to say something was going on, and given the context of what's good and bad. So we've already got that beginning point of it. So with that mean, we're looking at like the average, the norm for the values, that central measure of central tendency overall. That what are we normally seeing? And really, this is kind of like getting your average, and we're just looking at adding up all the values to get a total and dividing it by how many you've seen to get an overall value. So the mean, use the mean to describe the sample with a single value that represents the center of the data. Many statistical analyses use the mean as a standard measure of the center of the distribution of that actual data. So you can kind of see that from this clump of data we're looking at, that, well, we've got far outliers, we've got the central mass, and we may not know exactly what's going on, but the mean then tells us roughly, what's the norm that we're seeing. It's not everybody. It's not those outliers from the far side. It's not from here, but what's the normal we're kind of see, and then kind of go from there. And being careful about that sometimes those outliers can push it in different ways, but we have a feel of getting that central tendency of what's going on with the overall data, and then making a somewhat judgment based upon that. So if we go back to our data we had originally with the overall class, the 40 students, so 100 marks. And so here, first step is sum up all the data. So we get 1,828. And then we divide that by the number of students by 40. And so we get 45.7. So that means the average, so the test out of 100 marks, the average or the norm based upon the mean is that kind of getting 45.7 marks. Now, we don't know this being perfect, because maybe there were some higher marks or lower marks, these outliers, that kind of pulled in one way or the direction. So, but we know this is roughly kind of a norm. We can kind of start going from there. If we go back and then say put this on a number line, and having that spectrum again, once again, of not so good to yay, being good, of 100 marks, and putting some context. And if the norm is 45.7, you're like, okay, if I only had that to describe the data overall, you're like, I don't think the class is doing so good. It's kind of neutral to below, kind of some low grades, and it's not the best. But we know we don't want to use just one thing to start describing stuff. We should start using more, because how do we quantify that difference and see what else is going on? We need to combine this with other statistics. If we go back to the graph, you can kind of see this as well, that we'd probably be missing stuff if we didn't use more stats that pulled out other things, like this bigger clump that we see here of these twos, that it's probably not doing so good. So what's going on there versus this upper part that's right here? What's happening? And we're missing out, but we still see it's kind of a norm that we have kind of this left side, this right side doesn't equally distribute them across here, but gives us a beginning feel for what's happening in the class. Because yeah, there is this is closer to this bigger clump, so it's not like the class was doing the best. There's some upper people who are doing good, but a large chunk weren't overall, so something's going on. So we need to step and kind of use some other descriptive statistic tools and measures of centrality to see what else is happening and get a better feel overall. And so that's where we can start throwing in things like the median. So the median is the middle value. So unlike the mean that could be calculated, it won't be actually one of your data values. It just kind of gives you centrally where things are going and what's the normal based upon the data. The median will actually be one of the values that you put all the values in order, and you pick the one that makes it so that half the values, if your measurements are on one side and half the values are on the other side, and gives you that kind of measure. So it'll be one of your actual data values and give you a different feel for what's going on with the data. Combined with, we look at the mean and the median together, we can then see what's the norm between these two and which one's a better case and what's going on with the overall data. And so we see here again, when I was talking about that 50%, is that the median won't equally say that, well, values less than it versus greater than it, that it equally distributes them. But the median, it does all the time. If you were told that I have a median of X, well, then everything that's lower than X, that's 50% of your values you measured, and everything that's higher than X, that's 50%. And you can start interpreting more of that actual information. So it's a halfway point in between. So if we go back to original example of those scores the students got on that test, I've now ordered them from largest to smallest. We can see with 0 going up to 95. We can see we have some extra values that, like, hey, there's a couple of 22s. So that's 4 people who got 22 on the actual test so far. And, okay, well, I need to find the halfway through this. And so if I got 40 of them, the way you can find half is splitting it. And so you just divide it by 2, or timesing it by 1/2. And then you get 20 from that. So it means we have to find a value, like out of here, we need to count up and get it so that'll be 20 values on one side and 20 values on the other side, and it splits it right down the actual roughly middle. So to make this a little bit easier to see, I've made a grid overall, and you can see, okay, we'd start reading it by the top left here, and say, okay, that's the first number, and we keep going, reading from left to right. When we hit the end, we'll jump back down to the next row and lead left to right, and so forth for all numbers in order. And so here, when we know the halfway is 20, so we just need to count up. So, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm not going to count to 20 because you get the point. This is 10 here, so this will be another 10. And so this would be your halfway kind of mark. And so we see, okay, well, this specific value, that's 36, means, okay, well, that'll give that there is then 20 values or measurements that are lower than 36 and 20 values that were measured in our data set that are higher than 36. And it'll be split it evenly. Now, to make that easier to see, I've actually shrunk down, made the font a lot smaller, and you can see once again all the numbers that we had with their data value. And we can see our median value, and the idea is, okay, well, it's found by median, like supposed to be like sort the numbers, largest to smallest, go up halfway through, and so that's the 20th number in, so you just can count up from 20. You can pause the video here and validate it yourself if you would like. But we see we get up to 36, and so we will have roughly here, like 20 values here and 20 values coming afterwards. And so what we can start saying now is, okay, good, well, this is 50% of our values fall between 0 and this 36, and then 50% of our values fall between 36 to 95. And that's on this overall range, and then giving the median. And what gives it more of a context, when we go back to the context that we're working with, if we go back to that number line then of the lower values we could have and the higher values and put that median in place combined with our mean, well, we get a little bit more, that we get this 36 that's right here, and we know, okay, half the data is here to the left, and now the other half goes from here up to 100. So we have 50% of our data points, so 50%, and that's half, so that's being 20 students. So 20 students got scores between 0 to 36, and another 20 got between 36 to 100. Like, that's not good. That's showing that something from right here, that there must be a large clump of people. Like, this is a smaller range, only 36 marks, but yet half the people got scores within here, versus from 36 to 100 the other half. And so it tells us a little bit more information than the mean. The mean said, well, probably still not doing good distribution, but combined with the median, we're like, no, like, it's even lower, and there's probably a larger clump that's pulling it down to the left, because there's more people down here that had that score, and there's probably a few higher that were pulling the mean, kind of giving that tail and skewing it to the other side. And that, like, well, it doesn't seem so good for the spectrum we're looking at. And we can kind of see this easier if we go back to the actual graph of the data and still working with those values still along that same line, but we can really see, okay, that's why, like, there is a bigger clump that was within here, and those values were saying that to us, that we can split it in. So half the class go between 0 to here and going above. And it gave us now a better way to quantify and talk about that instead of just saying like class is not doing so good. We can literally say the range from like with the 0 to 36, that's half the class of 20 people that got this lower score and then above. But it doesn't really allow us to say, okay, well, where are those clumps and talking about that? So we need to include some more statistics into that, and we need to build upon that, because we don't always have cases where we can graph out all the data and just visually see it like this. Sometimes we can only look at the actual overall numbers. And so when we're looking at something on this spectrum, we have to realize, well, the only way that this mean was here was the skew that was happening down this direction versus like something that's happening here. So if we're seeing this separation, then well, maybe this may not be the best way to that central tendency, central norm of what we're expecting to see, and maybe the median is better. But we need more things to help tell us that, but we know there's some other clump that's going on with this actual data. We can like visually see here. So we need to add something extra into this and build upon that. So other things like with the mean and median is like the mean and median both measure central tendency, but unusual values called outliers affect the median less than they affect the actual mean. So remember that original example that was from the earlier video that talked about Elon Musk's like overall money making versus like lower cases, that you're like, no, these upper outliers will like pull that mean to the tail. And if we get these skews where there's like only a few here and one large outlier that's pulling it up versus the other, then well, maybe mean is not the best measure of central tendency in that case, and we should be looking more at the median value within this actual terms. And this is when we get into later on with mode that we can start looking at things like mean, median, and mode to tell, well, where are these unusual values and what's happening and which one would be the best one to actually like use to measure that normal and get that feedback and understand the information. And especially like if your data is like not symmetric and it's skewed, we'll need to do that. But if it is symmetric and they're all rough the same, then then we can just compare them. But we'll see that when it comes up. But I want to step into next is into mode. And here now, mode is different than mean and median because it's more looking at like how many what occurs the most. That's the kind of question that's answering is like at essential, which things appear the most overall. And sometimes you only have like one value, and some other cases you could have multiple times that something matches up the same. It's like example with this data here is, well, 2 appears twice and 5 appears twice, and there's nothing else for the numbers. So, oh, there's 2 modes. They match up. That's 2, that's got 2. And so there's 2 modes that are coming out of this and kind of telling us that there's like 2 peaks that are happening within here. And it gives us something, it's called the bimodal distribution. And the mode kind of tells you that information and can be combined with the actual rest of them. And so the mode value is that occurs the most, and like the mean and median require calculation looking at all the data, whereas the mode is determined by just counting the number of times each value occurs. Like the example that you see here, that up here at the top, like, well, I get some 6s, I can see 9s, 5, 3s, and so like, the lowest number I'm seeing is 3 and the highest is 9. So what we could do is draw a number line here and pick one number lower than the small, so 2, and then the upper one to be larger than this, and then just each time I see a number, just making a tick. Okay, well, 6, check. 3, check. Okay, 9, check, and so forth, and tally all those up, and then just look, which one do we get the most checks for? That's 6. Okay, that's the one that occurred the most. That is the actual mode right there. It's not too bad. And the other nice thing that comes out of the mode then is this idea of being able to combine it with the mean median and telling, well, what side is data listing to? Is it all the same? Is it there more data to the left? There's more data to the right? So these clumps that, like, say if we had these graphs, we can see easily, okay, yeah, this one's got more of a clump over here versus this is in the center versus this is to one other side. And we can see it in the graph, but we don't, again, always have that. We can just have some of these descriptive statistics, and then we can start then comparing the mode, median, and mean to each other to get another overall feel for what's happening. And we're going to see this in a second, how you can compare that. But, like, these become important by, like, well, okay, how do I determine then, is mean or median the best way to measure central tendency versus one or the other? And even from these graphs, we can quickly see what's happening. Like, okay, if they're all the same value, they're all the same. We can use either one, but say if it's more skewed to this one other side, we can see, well, this one here, this is the mean, like, there's a lot more clumps on this other side, so this is not really exactly what's the norm. More the norm is down to here, and the median is closer to that. So maybe we should be using the median as a better case of saying what is the normal out of these cases overall. And we need to then tell where that skew is. So we'll see that coming up from here. Also coming from the mode, we can start giving information back of how many peaks there possibly within the data. And that becomes an easy thing by like, how many modes did we have coming back when we calculated it? That if we have more than one mode, there's probably more than one peak. And so, and that means like balancing up, like even when they match up, but like if we get one mode value coming back, it's probably a curve like this where there was just one highest value that was overall versus another one where maybe there's these two peaks or maybe they're exactly the same and so it's the highest mode, so maybe we're getting like this bimodal that there's two larger clumps that are coming out of it, or it's spread across and there's a bunch of them, versus a multimodal, which is these extra peak, and say we're getting three separate modes that are coming out of it. And so it's just another way to tell what's happening. And also something we take into account that maybe getting bimodal distributions fine for what we want, but maybe we want more like unimodal that may be skewed to either side. And if we don't have that, maybe something's going wrong. Depends upon the context we're working with. Or maybe it's perfectly fine to have these extra peaks. An example where it could go wrong, if you're doing some research, say if we started with a bank manager. They want to know, like, what are the wait times for different services when customers are there? Because, like that can impact it. If it takes way too long for customers to wait, they're probably displeased and maybe they don't want to stay at the bank, or how many things you can handle within a day. So let's say like a bank manager collects wait time data for customers who are cashing checks and for customers who are applying for home equity loans. Applying for home equity, but home equity loans is going to take a lot longer, and the people who are waiting for that, if they're in line, are going to be there for a lot longer period of time versus someone who's cashing a check. You probably get like shorter wait times versus the other one would be longer wait times. And so because these are different services, the waits can include two different modes, because like the most common wait for the home equity loan line versus the one for cashing checks is probably completely different. And so in this case, maybe the data should have been collected separately and not compared all together. So only collect one population of data for the wait time for the home equity loans versus customers to check, and then compare those separately to see what's going on. So depends upon the context again. So let's go back to our data and give better context for going back to the test and those students and seeing what our actual mode is. So to do this one, I then once again just organized all the data from smallest to largest, because I know if there was the same values, they're just going to clump right together. It was easy to spot. And then I just scanned through it, and every time I found one that matched up, so a number appeared more than once next to each other, I just highlighted all of them right here. So 14, 44, 36, 22. And then out of all those highlighted, I then looked which one counted and which one had the most in it. So in the case here, 22 appeared 4 times. And so that's the largest one that appears the most, and that becomes our mode. So our mode for this is 22, and there isn't 2 modes from it. We can see looking at the rest is like, well, okay, there's only 2 14s, 2 44s, and 3 36s, and okay, there's 4 of these, there's more of it, so there's only 1 mode coming out of it. Now, by chance, let's say if we had another 36 in there, so we had 4 36s and 4 22s, that means that we'd have 2 modes, and we'd have 2 peaks. So one peak of most common of a group of students that got 22 out of 100 in the test, and another peak where 36 out of the test. But in this case, we only got 1. So what I can say is, well, the mode is 22, and so the most commonly seen like score that people got was like 22, so frequency. I forget like from the mode from it, so it's not just still a wide range coming out of it. But we have a unimodal distribution that it's just one kind of peak, and then there's some smaller peaks overall, but one thing that's dominating it. So now if we go back to our original number line and now add in the mode, we're kind of get stronger that something's going on, and we're going to get more skewed data. That if we're going across here, we see this peak here again, like, okay, well, we've got these 3 values, and it's still not looking good because at 22 out of 100, and most frequently seen one. Again, that's not good. And we have more ways to quantify this. We know, like, well, median, we have half the data here, half the data here. This is central tendency from this. It's probably skewed here. And the one that we're seeing most frequently so far is 22. And all three of these combined together is saying that, no, this isn't good. And there's these clusters more down to this other side. And what we're getting is this grouping. And coming up, we can see, like, even the differences between these values itself. We can start talking about, well, what is the skew that we're getting out of this? So going back to the graph, we see it once again. It gives more of the information of this skew of what we see for the actual overall data. We see the median. Now this one down here, just to be noted, is that to make this graph easier to actually see, is that mode probably should be noticing a peak. We have a higher peak that's up here on this graph. It doesn't seem to be that, but that's only because of the way I've gathered the data, is that I've clumped them in here, that 21 to 30 is all gathered together for the actual stats to make this graph easier to look at. Didn't make it look so jittery. And so really there is a peak here, and like this summary is every value between 21 to 30. And so it still does fit in that this is a peak and there's other values around it that they would have been the ones clumping up right here. So now a stronger way from saying the mode, that's just that frequency, and mentioned skew before, is that we need to tell, well, how is it distributed? How can we know which is the best measure of central tendency to actually use? What do we do with that? And so this is going to be more now of like comparing the mode, mean, and median, and just comparing those values kind of gives us feedback on how is the data distributed. It's skewing to one side, saying more of lower values versus higher values, and what can we say? Now, if we compare this, and if we say look at one in the beginning and say if they're roughly equal, so again, this equal sign that's squiggly is just to denote that we don't have exact equality. So it's not like 1 equals 1 equals 1 and 5 equals 5 equals 5. Match exactly as they can be slightly off from each other depending from the unit. So maybe the mode is like 1.5, the mean is 1.2, and the median is 1.7. They're slightly off from each other if this was like from numbers, and so they're kind of close. And so if they're kind of close here in the center, that means, well, okay, well, we have a symmetrical distribution that it's kind of more in this case and less coming like each side. And so in that case, we can really talk about the mean, median, or mode as interchangeable and pick the one that we want to because they're equally distributed. And so in that case, probably using the mean is good enough to talk about that central tendency. But if we get some other data that's listing to some different sides here, we can see, well, then we have a skew. So when a distribution is skewed, the mode remains the most commonly occurring value, the median remains the middle value, but the mean is generally pulled in the direction of the actual tail. Remember I did these outliers and Elon Musk and the money being made on this case. So that would be cases like, say, this one for the Elon Musk is that, like, okay, I've got the lower values that are pulling it here, and there's more, and it's pushing it. That these outliers, say these lower values, are pulling it down versus they're pulling this up here. Say like Elon Musk, fewer people here. He's making a lot of money, but there's fewer people making that versus more people making like less money down here. And so these skew and distribution, like they affect it. That if we just add that they're all roughly the same, okay, we can talk about central tendency, there's nothing different. But if it's skewed to one side or not, we need then to make a decision, okay, well, maybe the median is better than the mean to actually make that measurement of central tendency and what is the normal we're seeing. And also to tell us the direction where things are going, like depending how where these are here, that if there's less values here and there's more clumping on the other side, we can tell that by what type of actual skew that we have. And so it becomes important. So again, like in a skewed kind of distribution, then we have to switch the median being the best kind of norm that we're seeing, and we can use as part of an actual argument and get more information back by comparing those three to see where they skewed towards. So, for example, in building upon our statistical literacy and our vocabulary and everything that relates to this, is we've got the terms positively and negatively skewed, or like so positively or right skewed, and then negatively or like left skewed, kind of interchange for terms. And if you see that the mean is the largest value and the median and mode are generally smaller than that, then that means that we are positive or left skewed. And so we can see from here that it means that to the actual left, right here, there is larger clump of data, and then we have the mean going down here, which will skew that data this way, is that those other values are pulling that mean downwards. And so it means like, okay, mean's larger, it's going here, that we say it's positively or right skewed, and that tells us, okay, then the median's probably a better case, and there's probably more data clumped towards the left side of what we're looking at versus the actual right side. Now, if we get the opposite, where the mode is the largest value and generally the mean is the smallest with the median, then that means, okay, well then here's like where the mode would be, and roughly the median being down here, and the mean would be down here, and so it's being pulled more towards the smaller values. So again, we would start looking at the median being a better central norm to look at versus the mean, and then we know that there's more data clustering towards the higher cases. So, if we had that with our students for a test, that would mean, okay, well, we don't use the mean, we use the median, that's right here, and okay, well, that's going to break stuff up and give us a better measurement than stuff that's skewing it where there's less people down here. But then we can also say, okay, because this is happening and it's skewed, negatively skewed, that means that we have larger values that are clustering up at the higher, and people will be doing better. Okay. So once again, let's go back to our original example of those students and how they're doing. And we've already calculated the mode, median, and mean together. And now we can just compare them. And we can see that the mode is less than the median, is less than the mean. The mean is roughly the largest value. So it means that we are positively skewed. That, again, the data is being, like, this tail is coming down towards the 100 from the overall mean and being drawn this way by some outliers for stuff. But it's not a good, like in this case, was like we're being pulled out here, like this is larger, and the difference between them with this context is significant, that we're roughly like 10 marks in between each of these, and out of 100, that's quite a bit, I would say. And so we are definitely like positively skewed, and like in this case, we probably shouldn't be looking at the mean as a case of talking about what's norm. We should switch down to the actual median. And now, based upon that, I can make my argument, okay, it's positively right skewed, it's a large enough scale, I can't use the mean as the norm from here, so I will use the median, and the median is 36, and so now we have a better way of quantifying that. Okay, yeah, definitely this class is not doing good. We're down in these cases. Of like more, like 50% is between that 0 to 36 versus from 36 to an actual 100. And with that mode, and knowing that that's smaller, we know that's positively skewed. Right here is that there's a larger clump of data that is over here. And we can say, we can make those arguments based upon the actual mode. And we can see that again coming from like this case. Maybe it could be confusing right now. I know there's been a long video and talking about it, and we still got a ways to go, but there'll be even more practice with this, and I suggest you go back and do some more reading and looking at the videos as well.
Hi, I'm Adrienne Hill, and welcome to Crash Course Statistics. So in the last episode, we talked about the middle of sets of data, what statisticians call the central tendency. Today, we're headed to the data on both sides of that middle, what statisticians call measures of spread. Not to be confused with the gauge of the quality of my peanut butter and jelly sandwich. Measures of spread, right? Get it? Because you spread the peanut butter and jelly? Anyway, statistical measures of spread, or dispersion, tell us how data is spread around the middle. That lets us know how well the mean or median represents the data, and how much we trust conclusions based on the mean and median. And I can hear you saying to the screen, come on, Adrienne, when would anyone use this in real life? I may or may not have said that too at some point. I have no official comment, but measures of spread are all around, from test scores, like when you find out you scored in the 99th percentile on the LSAT. Economists use measures of spread to study income inequality. Investors use them to try to identify price bubbles they might want to try to avoid. Gamblers use them to try to figure out how much they might win or lose. Pollsters use measures of spread to help calculate margins of error. So yeah, they come up in real life. And heads up, there's some math coming your way. We're not going to spend a lot of this series doing calculations, but for this one, it's important. Let's do a thought experiment to compare measures of spread. And since you're probably watching this on YouTube right now, we'll talk about YouTube viewers and their ages. You're a YouTuber with big dreams and amazing content, but as a growing channel, you need to know more about your audience. YouTube will give you some information about this, usually in the form of a fancy chart. One of the pieces of information you could calculate is the range of your audience's age. Range takes the largest number in our data set and subtracts the smallest number in the set to give us the distance between these two extremes. The larger the distance, the more spread out our data is. With the range, we're able to quantify the distance between our most extreme points. We can often sense that groups are different, and our ranges confirm it. If we looked at the range of your audience's age, we'd get a better idea of the full spectrum of the people who watch. If you have 13-year-olds watching, you might want to limit the adult content. But if you have people over 40 watching, you may still need to explain some of the slang you're using. #lit, #fam. Am I doing that correctly? But the range won't tell you about your core audience. These are the people who you appeal to most. This might be better summarized by the interquartile range, or IQR, which doesn't consider extreme values. The IQR looks at the spread of the middle 50% of your data. So in this example, the ages of your audience. The IQR will give you a better idea who is the primary group watching you. A lifestyle guru like Bethany Mota might have an IQR of 13 to 25, whereas I might guess somebody like John Oliver has an IQR that's older, maybe in the range of 22 to 40. Their overall range could be similar. I'm sure there are 13-year-olds and 60-year-olds watching both of those channels, but the IQR gives us a better idea of their core audience. So let's introduce some numbers and do a little math. Let's say 10 basketball players have scored the following number of points in the first part of a game: 1, 3, 3, 4, 5, 6, 6, 7, 8, and 8. The median is 5.5. That divides the data into two halves. To divide it further into quarters, we find the median of each of those halves, which are 3 and 7, Q1 and Q3, respectively. The four quartiles here are from 1 to 3, 3 to 5.5, 5.5 to 7, and 7 to 8. The IQR is the difference between Q3 and Q1, or in this case, 7 minus 3, which is 4. If the median is closer to one of the ends of the interquartile range, it means that quartile has a smaller range. Since each quartile has the same number of data points, it means that for that quartile, the same amount of points are closer to each other. But we're still losing a lot of information about how spread out all of the data is, since only 2 of the data points are being used to calculate both the range and the interquartile range. There are measures of spread that include all of our data, just like the mean. Take the variance, which can give us a better sense of how spread out the whole data set is. Let's take a scatter plot of all our data points and draw a straight line across the graph at the mean. Then draw lines from each point straight down to the mean line. Those lines represent the deviation, or difference, from each point to the mean. Now imagine a square with sides the length of the deviation line. The area of all the squares for every point divided by the number of data points is the variance. But it turns out that if you use this same formula to calculate the variance of a sample, it would be biased. That is, the sample variance would consistently be a little smaller than the real variance of the population. We divide by the number of samples minus 1 in order to get the sample variance to be unbiased, or a better guess for the population variance. For example, say that the Mets, the Yankees, the Angels, the Dodgers, and the Astros have 2, 2, 5, 8, and 8 wins each. The mean number of wins for the group of teams is 5, 25 divided by 5. To calculate the variance, we take each number and subtract the mean, square this difference, then add all of these squared differences together and divide by the number of data points minus 1. The variance of this set of baseball teams is 9 plus 9 plus 0 plus 9 plus 9, all divided by 4, which equals 9 squared wins. And yes, I know 9 squared wins doesn't mean anything, but when we square our numbers, we're also squaring our units right along with them. Even though squared wins isn't an understandable unit to us, the variance is still a really useful number to have because it tells us how much variability is in our data. In our baseball example, it tells us roughly how far each team's win record is from the mean. We'll see it pop up quite often once we get to inferential statistics. For now, let's go to the thought bubble. Professor Hooch has hired you to analyze students' broom speeds for the Hogwarts Quidditch teams. There are 15 new Gryffindors, so you measure how long it takes them to fly around the field twice. And here's the plot of the times. times in seconds that it takes each student to complete the trip. Looks like a few of the Muggle-born students who didn't grow up using magic brooms took a lot longer than their classmates who grew up in wizarding families. Our mean of all students is 36.47 seconds, but if we take out the Muggle-born students, the mean is down to 29.67 seconds. Means are very easily changed by extreme values, but the median doesn't change as much. It only goes from 30 seconds to 29.5 seconds when we pull out the Muggle-borns. The range changes greatly, going from 46 seconds to 20 seconds because the extreme values determine the high number in our range calculation. The variance is also greatly affected since those slow Muggle-born students inflate our mean. If we take out those Muggle-born times, the rest of our data is quite close together, reflected in the variance of about 36 seconds squared. But once we add those times back in, the variance shoots up to about 228 seconds squared, which matches our intuition that the group is now more spread out. You can see that the distance between points and the new mean are much larger than before we put the Muggle-born times back in. These Muggle-born times change our measures of spread and center, but that doesn't necessarily mean these data are bad. We need to think about whether unusual points belong in our data or not. And we'll talk more about unusual points, or outliers, a little later in the series. Thanks, Thought Bubble. Remember that the units of variance are squared units, like seconds squared for our flying broomstick times, or baseball wins squared for our baseball example. And yes, variance is valuable, but sometimes we need something with units that make just a little more sense. Enter standard deviation. The standard deviation is the square root of the variance, which gives back the units that we're comfortable with, seconds or baseball wins. The standard deviation of our Quidditch data would be about 6 seconds without the Muggle-born data, and about 15 seconds with it. You can think of the standard deviation as the average amount we expect a point to differ or deviate from the mean. That means that on average, we expect students to deviate from the mean time by 6 seconds. When the Muggle-born students raise our mean, our standard deviation goes up as well. In part, this happens because now the other points are further from the mean, since the mean became larger. Just like the mean, the standard deviation and variance are heavily affected by unusually large or small values. So you should still always look out for extreme values in your data, and be aware of the influence they can have. If you see someone reporting on a mean number in an article or on television, you can use the standard deviation, if they're thoughtful enough to give it to you, to get a better understanding of how well the mean represents the data. If the mean number of murders per state in 2015 was 307, which it was, then a standard deviation of 10 murders shows us that 307 is a pretty good guess for the number of murders in any individual state. But if the standard deviation was 353 murders, which it was, that guess wouldn't be nearly as accurate. And this makes some sense. You wouldn't expect Montana to have nearly as many murders as a heavily populated state like New York or California. So let's go back to our YouTube channel. So now you have a better idea of who's watching you, and you're getting more and more viewers every day. If you want to grow more, you realize you need to diversify your audience. So you look at the standard deviation of the ages of your audience. This will give you a better idea of whether your audience have similar ages or whether you're appealing to many age groups. You keep adding new content and collaborating with other YouTubers to try to reach a wider audience, and it's working. Your standard deviation is getting larger, which means you're attracting a more diverse or more spread out audience. And congratulations! Looks like you just hit 1 million subscribers. As our YouTube thought experiment showed us, the different measures of spread each give us different information about our data, but they all tell us something about how spread out the data are. Sure, you can use measures of spread to grow your YouTube channel, and they're important for statisticians, but they're also valuable for us non-statisticians to ponder. And I'm gonna go a little deep here and try not to veer into the cheesy, but here's my big takeaway from this episode. We all have a tendency to compare ourselves to the average. We compare our income to the average income. We compare our rent to the average rent, our intelligence to the average intelligence. We compare our weight to the average weight of someone our age, and on and on. From these measures of spread, I take away the idea that the average whatever on its own can be deeply misleading. Comparing ourselves to that single statistic can give us a false sense of failure or success, depending on how the data is spread out. So maybe stop comparing yourself to the average. Or if you're really insistent on ranking yourself against everybody else, go calculate the standard deviation too. Thanks for watching. I'll see you next time. Crash Course Statistics is filmed in the Chad and Stacy Emigholtz studio in Indianapolis, Indiana.
So that video gave us a good background on what you can combine by combining those central measurements and what's the normal with how it spreads out and how they need to be combined together. And you can't just work with one value. And we need to combine together to see what's happening overall. So, so the measures of spread and the purpose. Like the purpose of identifying the central value of what is the normal describes it's a typical value you're seeing from there. And once we know this, we can then measure the amount of dispersion or spread that we have based upon that, and from that central to tell what's going on. Is like everything clumped together, or is it further out from what the norm? Because if it was like really close together and not dispersed, and this is the norm, then like I say, if it's our class case, a lot of people weren't doing good, or was it spread out a lot, and there's a case of people not doing good, but there's still some people who did do good, and we need ways to talk about that. And so we're calculating the spread that's going on overall, and there are three main like measures of dispersion, being range, variance, and standard deviation. And for this course, we're going to stick with range and standard deviation predominantly, and then we'll kind of look at that interquartile kind of range as well when we look at box plots or box and whisker plots, which are throwing a new descriptive graph that helps us visualize the data a little bit differently, so it's not so cluttered when we're looking at everything if we're presented it. And so the range is a very easy thing to figure out. It's really just find the smallest, find the largest, and subtract the smallest from the largest. And that tells us, hey, well, what's the smallest value, what's the largest value, and how many values are there actually in between from our actual data versus the possible range of values. So, you use this to understand the dispersion, really, is that like if you have a large range, depending on the context where you're looking at, then it means the data is really spread out, versus if it's a small range value, it's very clumped, goes together. And this determining large or small depends upon in the case that we are actually looking at. So if we go back to our original one that we've been working through for all of this actual data, where we have the 40 students out of 100 marks, and we have all of our data here, we can start calculating the range. And I've done that by just sorting all of the actual data once again. We can see the very first value would be the smallest. And so we get 0, and the largest being 95. So our range is 95 minus 0, which equals 95. And so like we have a really big distribution because we have a total of 100 marks, and the smallest value we can possibly have is 0, and the greatest value we can possibly have is 100 in this context of being a test. So that range like is huge over this case. So we have a really big distribution, spread of actual grades that we're getting. We still know that, okay, well, generally we're going to feel that the class is not doing good overall on this test, but we know, okay, well, it's spread out. They're not all clumped around the really low grades, that there are some outliers that did better and giving a wider potential of what we've got. And so we go back to our original number line again, we can then see then if we add in the actual range with the rest of the values that we've calculated before this, we can now see, well, the lowest value is 0 and the highest value is 95. And which is nice. So if we're given this range and we have that drawn out, we can then say, okay, well, I know lowest is 0 and it's up to 95, and there's nothing greater than 95. And then we can start combining these with that measure of centrality. Like if this is dispersed really going out, we can then look at the rest of these, and we already determined that we kind of have a right skew because the mean is larger than the median in mode, and so we get that tail that's going down this way, and so we know, okay, well, this is the tail, and so this 95 up here, that's what's pulling the being this outliers that are pulling the mean down this way and showing that, okay, well, the mean is not going to be, in this case, a good measure of what's normal in that central tendency, and so we need to look at the median then instead. And with the median then now we can say with this range, okay, well, 50% of the class being 20 students got between 0 and 36, and then another 50% got between, 36 to 95. So like knowing the range, we now narrowed it down that we know, okay, 20 students are within there. And then now knowing what the mode, well, we know that's going to be a peak that's within here that shows us, okay, well, there's going to be a larger peak in this range of not so good. So we're still sitting here that there's a larger clump down here of not so good marks that's really down to the spectrum that we don't like, versus up here at 95 that there is still something existing. That range told us that and gave us more information to be able to talk and quantify what we're getting about the class. And we can see this if we go back to the graph even more. Now, normally, again, we don't always have the graph, so we need to be able to compare the values in these ranges. But you can see now that between like these values of 95 to 100 and these clumps that we're getting, and we know from the largest to the actual smallest, that we can look at these and visualize what we'd see from that actual graph and use those numbers to compare to come to some kind of decision of what we're seeing from the overall class and getting more deeper kind of into what's going on. Now, all the stuff that we've been seeing before this has been kind of cluttered, if you notice. Like, there's so many values and things that are going on here, and in between and overlaying it, that it may start getting a little bit confusing. And so this is where, like, combining with other charts and stuff would be nice. And for this course, I just want to bring in then box and whisker plot, or sometimes also called the box plot. And it's a nice way of combining the actual like range that you're looking at, your minimum value, your maximum value, you have your medium, and then you can get to that interquartile kind of range of, okay, well, where is a larger clump, and narrowing down that clump within the spread that we're looking at, and knowing that we can talk about these extremes and then narrow down to what's the core of what's really happening, and even have a better way to visually see the actual skew that's going on overall. So before I go into explaining it more, again, I want to go into another video. And Khan Academy is always super useful, and if you haven't heard of it, it does a lot of stuff with math and other free tutorial videos, so it's a nice way, like I suggest, to go if you're looking for anything math related, to get some extra tutors hands-on.
An ecologist surveys the age of about 100 trees in a local forest. He uses a box and whisker plot to map his data, shown below. What is the range of tree ages that he surveyed? What is the median age of a tree in the forest? So first of all, let's make sure we understand what this box and whiskers plot is even about. This is really a way of seeing the spread of all of the different data points, which are the age of the trees, and to also give other information, like what is the median and where do most of the ages of the trees sit. So this whisker part, so you can see this black part is a whisker, this is the box, and then this is another whisker right over here. The whiskers tell us essentially the spread of all of the data. So it says the lowest data point in this sample is an 8-year-old tree. I'm assuming that this axis down here is in years. And it says that the oldest tree right over here is 50 years. So if we want the range, and when we think of range in a statistics point of view, we're thinking of the highest data point minus the lowest data point. So it's going to be 50 minus 8. So we have a range of 42. So that's what the whiskers tell us. It tells us that everything falls between 8 and 50 years, including 8 years and 50 years. Now what the box does, the box starts at, well, let me explain it to you this way. This line right over here, this is the median. This right over here is the median. And so half of the ages are going to be less than this median. We see right over here the median is 21. So this box and whiskers plot tells us that half of the ages of the trees are less than 21, and half are older than 21. And then these endpoints right over here, these are the medians for each of those sections. So this is the median for all of the trees that are less than the real median, or less than the main median. So this is the middle of all of the ages of trees that are less than 21. This is the middle age for all of the trees that are greater than 21, or older than 21. And so these essentially are splitting, we're actually splitting all of the data into 4 groups. This we would call the first quartile. So I'll call it Q1 for first quartile. Maybe I'll do 1Q. This is the first quartile. Roughly a fourth of the trees, because the way you calculate it, sometimes a tree ends up in one point or another. About a fourth of the trees end up here. A fourth of the trees are between 14 and 21. A fourth are between 21 and it looks like 33. And then a fourth are in this quartile. So we call this the first quartile, the second quartile, the third quartile, and the fourth quartile. So to answer the question, we already did the range. There's a 42-year spread between the oldest and the youngest tree, and then the median age of a tree in the forest is at 21. So even though you might have trees that are as old as 50, the median of the forest is actually closer to the lower end of our entire spectrum of all of the ages. So if you view median as your central tendency measurement, it's only at 21 years. And you can even see it's closer to the left of the box and closer to the left, the end of the left whisker than the end of the right whisker.
So you can see even from that, like being able to read those is valuable, and you'll see that pop up as an artifact in some like other cases, but also to easily represent the data. Like if you were given that, you're not given the data, but you're given the other descriptive statistics and you're given that chart, you can start interpreting quite a bit from that and pulling out quite a few values. And visually, it also shows you a lot of extra things. So again, the box plot, or also a box and whisker plot, also called a box plot, displays the 5-number summary of a set of data. The 5 numbers is the minimum. The first, so we can see from that, is the minimum value. Here, this range being the first quartile. So from the min up to that first line. And then from the first quartile up to this next line, it gives us the median. So splits up half and half between this overall. And then we get between the median to the actual third quartile, and then we get the fourth quartile with this range, and then we get the max value that's right here. And what's very interesting from this is that if we have these values, if we subtract the third quartile value from subtract the first quartile value from the third quartile, we get that IRQ range. So this kind of narrowing down of a range instead of just the min and max we can talk about. We also have this inner range, which is saying is a lot of stuff is clumping within this actual case. And so narrowing it down and seeing what's going on overall. And this quartiles I'm talking about, again, is dividing it in 4s is a key thing. And so when we're looking between to here and here, that means that this area is capturing 25% of the data. This is another 25, this is another 25, and this is another 25. And it doesn't mean that this will always be distributed equally, because what if there's a lot more clumps that are here, then that could be narrowed down. So overall. So it's a nice way of summarizing everything that we're actually doing and quickly getting information out and seeing that visually. You can see that here. Again, the lower, upper, bounds, everything. So right, remember, we get this one chart that does a lot. And what's nice is that then we can compare this against other populations really easily. We'll see in the future. A third thing is if we go back to those skews where we were normally also looking at comparing the mean, median, and mode, and seeing which is the best measure of central tendency, if we should be using the median or mode, is that having these box plots gives another visual indication coming back to us. If it's flat and uniform, then like all your quartiles will look the same. If it's bell-shaped and there's more in the central, those inner areas mean there's more clumping of data will show a smaller box. And then you can see these cases here, like we have this positively skewed where it's coming down here, or this negatively skewed coming down this other side. You can literally see that you will have like a larger outer whisker to the right versus to the left, and you know, okay, there's more clumps. And so right from that diagram, we can see there's more clumps, so we can back that up with the other data we get for the ranges, the mean and median modes, and all the rest of that. And then we know we can start quantifying. Well, now that we got that, we know there's a clump to that side. We can then say, well, okay, here's a starting point and give the interquartile range of that larger clump of what we expect. So say if this was, again, that YouTube channel kind of perspectives, we know, okay, here, if this was younger to older ages, it means, well, we have a larger clump of people that are younger. Versus, say, this one, getting younger to older, is that we're having a lot of people who are older who are watching our videos. So, and we can say that we have this exact kind of range to work with, so we can start targeting that more. So now we can even start quantifying that specific like skew that we actually have and get more specific argument and compare that with other data. So to make it again, like if you need to make, I'm not going to make, like if you need to make it within this course and it comes as a question on a test or featured in your exam, it's not so bad to do and you should take some practice. So first is just to figure it out, sort all the data you have from smallest to largest, find the max, find the min, and find the median. And then between the min value and the median value of that sorted data, you find the median of that again. You call that Q1. And between the median value and then the max, you find the median of that, and you call that Q3. And you draw the lines all connected together. Now, generally when it comes to tests or anything else, if I'm going to make you do this, I will just give you the max, min, median, Q1, and Q3 values. And then you'll know, okay, here's the whole range of the data. And then I would ask you to draw everything out as a way to demonstrate that you understand where all these values are. So if we go back to our original problem we've been dealing with from the get-go forever with this long video, that we have the test scores of those students. We know the min and max we've found before when we've sorted it being the 0 being the min, 95 being the max. We know the median we found out before is, sorting the data halfway through is 20th actual number, and we found that that was like 36. We see that here. And so, we've got the min, we've got the max, so this is going to be the outer whisker, this is going to be the min whisker. From right here, you have the median, and now from the median to the min, there should be roughly 20 values here. So half of 20 is 10, so we get right here, okay, well then 22 is the Q, the quarter 1 kind of value. So we get that range from 0 up to 22 up here. So, and that's counting 1, 2, 3, 10, like the usual way up to here. And so from 0 to 22 is where we have the first quartile, then we have the second quartile between here, the 22 to 36, then the third quartile up to here, and then the fourth quartile. And so same thing over here, we had 20 values, divide in half, counting from here, you get to 10, you get that 70 kind of range. And so you figured out all these numbers. Now we just have to draw the lines coming together. So once again, if we go back to our original line we were working with that we know for tests and in the context, the lowest you can have 100, lowest you can have is 0, we have 1 as being 100, and we know again from being lower, unhappy to happy scores, we can now get this box diagram. And if we understand all the values, it makes it a lot easier to see what's going on. Is that we can see, okay, the min, if we're reading it, okay, this whisker goes to the end, is the min is lining up here is 0, so lowest score we got on the test is 0. The highest score we got here is roughly here, so it'll be 95, we know that before. We could see reading from here. We know the median right here is 36, and we know first quartile is 20, and the third quartile is 70. And so this starts telling more of our skews, and you can see where it's showing it is like, okay, well, still spread wide because the actual range. We have this inner clump of the interquartile where you have the majority of people now between 20 to 70 within the class. But then we even have like a stronger concentration of those people between 20 to this 36. The median, this means that, okay, well, half the people are between here. And so now we can break down. We tell more of what's going on with the graph itself. And that idea of the quartiles is that, okay, well, we knew before that the median here was half the data, so 20 people had scores now between 0 to 36, and 20 people had between 36 up to the 95. But now we can narrow that down with the box diagram here, and it's fair with the quartiles, is, well, that broke it down not just to halves, but into quarters. And so now we know, okay, well, out of the class, 25%, so 10 students got between 0 and 20, and then another 10 students got between 20 and 36. It's a smaller clump. And then another 20 got between 36 to 70, and you can see, well, that's telling you a lot. Like here, there's like 10 students got between here in this smaller range versus 10 that got here. So we know based upon this that there's got to be a bigger clump that's going on here versus the rest of these. And so now we're digging down, and with this box and plot diagram and the interquartile, we have a better kind of concentration to say in a more quantified way of digging down and seeing what's going on without just using the one individual value. And so we can then now bring this all back together and bring all the stats that we've got our mode, median, and mean. And now we have the box plot diagram. We still contain within a range, so we can still see a range from 0 up to 95. We know that. We know this max up with the actual median. We have where the mode is. We have the mean is. We have determined that because the actual positive skew, that the median would be a better value to compare for central tendency. We know then, okay, we can say between 0 to 20 is 10 people, and 20 to this 36 is got another 10 people, and then we know again this median. So like we can see that this clumping that's happening over here, and we can start talking about that more, and we get a lot more going on with the overall data. And if we just had these and we don't see the graph, we can get a lot from this. And knowing that there's this peak that's right here, and there's a ton of people that's within this actual overall range, and this median, this class is not doing good, and there's a larger clump of people between this range, like quite a few that we can now break even just saying from this 36 to here to here. And going back to the graph, we can see how it kind of matches up overall and shows the similar thing that you can now, if we can visually see the clumps, you can go down to here and you see, okay, yeah, there is this half here and kind of half here, and look at, we have this like smaller case down here at the actual bottom, but that's like boom, like right here to right here, and you can see, well, that's why it's squished. There's a lot more people that got scores within that range and that skew, and we can tell more about what's going on. They're not doing good, and we can quantify describing everything that's happening to this overall. So you can see how these box plots will be very useful. Now, last, we're going to end off with standard deviation, which is always a good thing to look at. And this one is more in relation to the actual mean. So that box and whisker plot tied stuff a lot to the actual median. And so standard deviation relates more, again, about being spread, but more uniform distributions, and works better with the actual mean. And sometimes just gives different ways to talk about the actual data. So you use the standard deviation to determine how spread out the data is from the mean in both the left and right directions. And you can kind of see that from this diagram, that the key thing is that the spread is now tied more to the mean in this actual case. And if we had this nice distribution, and we have it from going to the right and the actual left, and these deviations kind of act as like steps as we're going through, like 1, 2, 3, 4, and just capturing this overall data captures everything. And then the idea is that, well, within that range, when we're looking at standard deviation, where we go from this left to right, we get this first clump here, which says, well, okay, that one deviation away in both the positive and next will capture 68% of all the actual data. And then we take another deviation, that'll be 95%, and then 99%, and giving us a feel for, okay, well, how does it spread out? And how big is this step here? If it's little steps, we're closer together versus spread out further on. So a good rule of thumb for normal distribution or symmetric distribution is that, again, we have that 68%. So this is, again, where, like, how can we talk about values that we can talk about the mean and the standard deviation and see where it spreads out, but maybe if the data is skewed too much, we should stick to the median and the box plot and whisker plot and see what's going on, but we still need to know how does the data spread out. And with these deviations of like how much does it clump and gather the overall data. And so knowing when we do one deviation out in the post positive negative and get that range, then we know, okay, well, first one 68%, then 95%, then 99%. So one step or standard deviation is equal to adding or subtracting the standard deviation value from the mean. So when we see that actual value we're getting back, that is just one deviation value. And to get the overall range from like the lower to higher within that first overall deviation, we need to take the mean and subtract the standard deviation, and take the mean and add the standard deviation. So subtract, add, and it gives us that spread out field for this. And then we do it again for like subtract more and subtract more to go for the actual next steps. Now, notation and symbology here is that sometimes in papers, in other cases, you'll see standard deviation abbreviated as SD. And sometimes you'll see it as sigma, another Greek symbol. Depends on the type of what you're doing of like a sample or overall population kind of standard deviation. We won't go that crazy in this course. But other times when you'll see mius and some other cases, you'll also see this little plus minus symbol, and it's a way of combining the mean and the median together when it's written, because like standard deviation, combining the mean and the standard deviation together is like, you can't talk generally about the standard deviation only. You got to talk about it in relation to the mean and adding and subtracting. And so that's why they will use that plus and minus symbol. And so if you see something like this, 15 plus or minus 4.5, how you interpret that, since we're in a stats kind of context, is, well, the first value is the mean, so 15, and the second value that you'd be adding to it and subtracting to it is the standard deviation. So, mean of 15 with a standard deviation of 4.5. Now, key of telling it and interpreting the actual number itself is like how big or small the number is. So let's say we take a look at this example here. An example samples from two populations, so two sets of data with the same mean but different standard deviations. So we have one population of data that's graphed out that's red, and we have another one that's graphed out and it's blue. And they both have a calculated mean or central tendency of 100. So it means the most common value you're seeing, and this is 100. And we can see the scale at the bottom of the graph is that it's going between 0 to 230. And so, yeah, you're kind of like, okay, both of them. And if we were saying, oh, the common between the two populations is 100, so they're just exactly the same. And you're like, you can see it's affecting. It's hard to compare those actual two. And so if we look at the standard deviations in between it, we can tell a little bit more is that, okay, if we have the red population here and it's a standard deviation of 10, then you'll be, okay, well, if we take one step of that deviation, and so we take the value of 10 and we subtract it from 100, get 90 for the left, and then we add 10 to the 100 and we get 110, that gives us a range kind of spread out between like 90 and 110. And that's one deviation. So it means that for the red population, between the value of 90 and 110, 68% of your data values fall within that case. And you can see that's kind of like where it looks like it's narrow. So like the closer this is together and the smaller that you have in relation for the standard deviation, the more that your data is clumped closer together and what you can tell about that depending on your context. And a key thing here is the standard deviation is the same units of what you're looking at. So when you're looking at, okay, it only has a deviation of 10, you have to look into the context of what we're getting here. So 10 here in this case is a smaller kind of step because we're going between 0 to 230, so 10 is a tiny chunk. But if we only had like smallest value 0 and the largest value is 20, a step of 10 to that, that's a really wide step, a big step you're actually taking overall. And so you have to be careful to remember that's in the same units of what your mean and the rest of your data. If we go to the blue in this other case, so it's still the same mean, but has a standard deviation of 50, well then to get one step here, we minus 50, get from 100 to 50. We add 50 to 100, get 150. So that means we now get this range of 50 to 150. And now that's where like 68% of the values for the blue population fall within here. And that's where you can see the big thing between the red and blue for these values that you're like, okay, no, red is very clustered in close to here and blue is very spread out. And now we can say more. If we only looked at the mean before, we can say, okay, hey, these two populations, the common kind of thing is about the same. But if we add in a standard deviation, well, they may look the same for the central kind of idea, but like the red group, we can tell more is like a lot more of the group values are clustered closer to that actual value versus the blue group, which is more spread out. So like they have some similarities, but this spreading out shows that there's something different going on. Like say if this was test scores and the test was out of 230, we would know, okay, both classes, they generally got the same average. But then if we compare them deeper, we know, okay, we're like, oh, the red class, a lot of people got around this halfway kind of mark into good and not really anyone higher than that. And so that's not good. Like, look at the difference. Like, that class didn't do the best overall where the blue, like that same average. And we got some people that got way lower scores than the red class, but we got some that got higher. And that deviation would tell us that more and tell us that spread, just kind of what we saw for that box kind of chart. So if we go back to our data and calculate everything from this, is that you can get a standard deviation of 28.81 using the whole population formula. So in this course, I'm never going to ask you to calculate standard deviation. I will just give you the actual value. And so you can assume either it was calculated using population or sample formula, if you know more backgrounds for stats, but just you have that standard deviation. And we already calculated earlier on that the mean was 45. So if we write down the notation we've seen before, is for our data, it's 45.7 plus or minus 28.81. Before we even go on to any of the next slides, you can kind of think, okay, standard deviation is 28.81. This is, context is with score of a test that ranges from values from 0 to 100. And you're like, oh, 28, that's like a quarter chunk of the actual data. And like, that's a big spread. Like that 28 is a quarter. So we're adding a quarter plus a quarter and getting like half like of the overall scores you could actually get like an entire test. Like, so this means it's really kind of spread out for the actual data if we're relating it to comparing the central choice being the actual mean. And if we go back to, again, our chart that we've been using forever, we can kind of see that we have the 100, we have your mean, median, and mode. And now compared to what we're doing the box whisker, where before we were comparing it, like connecting it to the median, now we're like, okay, standard deviation is always connected to the mean. That never changes. That's how you have the spread from the mean, versus that box plot helps tell stuff from spread when we're going away from the median. And so here then we take the 45.7 to get one deviation to the actual left. We subtract the 28, so 45.7 minus 28.81, we get 16.81. And then we take one deviation going to the right, and so we add the 28, and we get 45, blah, 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 we get 74.81. And so what this tells us is that between 16.80 to 74.51, that's 68% of the actual, like, the value. So that means 68% of the students in the class fall within that actual range with this divvying it up. And then the next we get more steps that spread out in that probability from right here. So it gives us more context of what's going on. We can start comparing to other classes. Now in this case here though, we've already seen that there's a skew, and we've seen that this is large enough in this context that, hey, the mean is probably not a good choice for the measure of what's common. The median was probably better. So we probably don't really want to look at the standard deviation in this case. We can come back to it and we can use in relation to the mean and kind of hope maybe it'll give us some more information that we're not sure about. But maybe we should go back to that box kind of plot to say, okay, where's the clumping happening a little bit more? Depends what we want to do. Just back up your argument from that data. So if we bring it in again into this context, you can then see again that, okay, well, the standard deviation, we know a better thing. Okay, well, from here to here with that data, again, like we now know that this clump overall is 68% of the class, and we have some lower outliers, the lower class, and lower the upper ones. So kind of like that box plot, we're seeing similar things we saw before. And we can even now clump all of this all together. Let's like smash everything we've been doing this whole time as I go crazier making this darn video. We get the box plot, we get the standard deviation, the mode, mean, median, we get all of that. We know the skews and all this, and then we can start seeing how things are different from here. We can still see that even with our standard deviations, this inner clump of the the box plot, that interquartile kind of range, still falls within that standard deviation range, but we see some stuff differently coming out of this. We can still see that, I don't know what happened right there. That was weird. Okay, never mind. I clicked something wrong and just disappeared for a second. And so we can see, like, well, okay, it's still ranging within here, but if we went to this median, this really tells us this one clump. It doesn't tell us more about what's going on. We know we have this clump, we know this clump, and this is why in this case for being skewed, that this still shows us roughly this range, but narrows it down a little bit more, that we know from this 20 up to like this range here, that we know the quartile values. It narrows down where we have this inner clump, and over here also tells us a little bit closer to where the bigger clumps are going on, and the fact that we have something going down here. So we can see that we could argue both of using the mean and the median values, and then if we went with the mean, the standard deviation, versus the median with this kind of box plot stuff, we're going to get similar kind of arguments. It's just that in this case, because of the skewed data and because it's so spread out a little bit more from those three values, that the better choice would have been median, and we can target and get more information coming out of this. And so, like, whoo! Deja vu. We're like way back at the beginning of this first example. I'm not going to go through everything again like that. You can go reverse through it if you want. But like, we started with this. We started with this data and trying to find patterns and seeing what's going on. And like, I can't tell a lot from this data. And so like, come on, powers of statistics and tools. Let this jump out to me. Give me some like vision and seeing what's going on. and like to give me some help to gather some information and visualize and see what's going on from this data so I can make some better decisions. And you're like, boom, and you're like, oh, okay, this doesn't seem so confusing. There's a bunch of stuff here, but I can start interpreting it. It would be confusing if I didn't know the vocabulary and didn't have any statistical literacy around this, but I can then now use what we've been building from our statistical literacy with this kind of context and hopefully get into some kind of quantitative and statistical reasoning to come to some kind of conclusion for how the class is doing overall. That we have the range that we kind of worked on. We have all these beginning values where we could construct these kind of charts from. We know it's positively skewed, and we know we have greater distribution. We know we have like the mean and the standard deviation, but we're like, okay, well, probably because it's like positively skewed, I'm going to go to the median to kind of separate this data. And we can see all these things combined together that tell us more information. Like this is all lined up, and maybe we don't have this graph, but we can look at this and still get an inkling of what's happening down here. And we can start saying, okay, well, look at this. This class didn't do good. If we look at the median, that splits up everything. We can see, hey, wait. We'll go to the box chart. Like the lowest score we got is 0. The highest score we got is 95 in this actual overall class. But then if we go to the median value of 36, well, we can say, well, half the class, being 20 people, had a score between 0 to 36, and the other half had a score between 36 to 95. Okay, well, that's fine. But then if we look at the box plot and go a little bit deeper with this, then we're like, okay, well, then, from 0 to 25, that's a quarter of the actual students. So that's 10 people. 10 people got between 0 and 20. 10 got between 20 and 36. And so there's this bigger clumping what's going on, and this clumping happening with this range versus then we go with the median that we had like now 10 students from 36 to 70. Like, whoa, what's going on? That there's this clump of these lower grades, and then suddenly between like 36 to 70 we only have 10 people, so it's very few. And once again from 70 to 95 there's bigger, and there's only this 10. So from here to here, like there seems to be more of a tail going on because it's spread out, and we can see from the box diagram versus on the box it's kind of clumped in closer to here. And so you're like, hey, they kind of in the context of what's good and this is bad down here and this is good, this class didn't do good, and we have these reasons to kind of say why and back it up and start subtracting some numbers and looking together. And but we had this before, and it was hard to come to the conclusions, know what's going on, narrow down and infer and pull out some more information, versus here we can start going more and asking other questions and seeing the power of the descriptive statistics and what's going on and reading these charts and building it up. And we're coming close to the end, only 2 more slides, and I wanted to come back to this thing. This miasma of numbers we had in the beginning that we can't tell what's going on. The matrix numberies again, and just seeing, well, there's only single digits, and what can I tell about this? I know there's no context, but I can't tell and understand any patterns, and how do I start inferring anything and gathering new information to build upon it? And well, okay, boom! Boom! Our descriptive statistics that we're getting out of it, and I can start seeing a little bit more. Okay, we got min, so the smallest value possible is 0, and the largest value maximum is 8, and we have a range of 8. And so I can now construct a number line. If I know the minimum 0, okay, I'll just go 0, and I'll make it 10 arbitrarily just as the maximum as a range. We know mode is 2, so okay, out of all those numbers, 2 appears the most. That median is 4. So we now know, well, between 0 and 4, that we have half the data. In between 4 and then 8, we have the other half of the actual data. And we have a quartile 1 of 0, and a quartile 2 of 6, and a mean standard deviation. We also know we have 608 data points. And so now we can start telling a whole lot more from this. If we quickly go to the box plot, we can see that whisker is not even extending. It's right on that edge of 0. So that means at 0, 25% of our data being 152 values from here is zeros. We have 152 zeros in that data. And then next from there, we have 152 values that range between 0 and this median value of 4. And then we have more quartiles. So 50% of our data is values between 0 and 4, and the other 50% is between 4 and then actual 8 overall. And we can break down this bigger case by the box of, okay, well, from there 4 to 6 is another clump. We have 152, and then we have like another 152 from 6 to 8. And so we're getting this kind of distribution, but we can see here that, well, it's kind of skewed, that they're clumped up at the higher, but there's a lot more that's going on. So we probably have like this clump going above. If we go back and even look, hey, is this data skewed or not? Which should we be looking at, the mean or median or standard deviation? Well, we look at the mode as 2, which is less than the mean, but the mean and the median are kind of close. It's not that far off. Like 0.14 when we're looking at a scale of 10 is not that much. And so these are roughly the same. And so you're like, well, okay, well, I've got the mode here between, and I'm like, well, these are kind of close. And so there's probably tiny little skew going over here, that like 2, but it's still in the central. So I could use median and mean to be interchangeable. So I can say, okay, yeah, like I can then look, maybe here I can look at the standard deviation to actually see the overall spread of what we're looking at. So we see at the bottom, so, you know, plus or minus, get that range, one standard deviation. So between here going down to 0, we have the 1.16, roughly down here going up to 3.6, that 6.63, that is 68% of the actual data falls within this this overall range. I didn't change this values enough from right here, but you know, like 304 values, 50% of the data, like we know like, okay, well, what we can do overall with that data. But you can see like I'm kind of rambling from the data, but like we had blah, blah, what is this, to like, well, here we can talk more, we can infer and pull more information out of this. And so you can see when analyzing that, like, this is the kind of stuff that you would get the end of measuring a dependent variable, and even more, like thousands to millions of like data points you could potentially get from this, and it's hard to see what's going on. And so by jumping into our powers of statistics and descriptive statistics, we can start seeing and like understanding it more, then apply it to a context and start making a decision and back it up with actual numbers and things that are backed up from there. So I hope you've made it through this. This is a longer video, longer than any we've had before this, but this is a very important topic, and I wanted to spend more time on it because more people feel fear and confusion from it. So I'm hoping that there's been enough examples that have helped you. Now, I'm not done here for examples. This is just explain to giving an idea. So now you're going to see a follow-up of a bunch more examples that give some idea of a context and just give you some of the stats. So you don't have to calculate it, but give you the box diagrams or some of the data, and then you maybe need to construct the actual box whisker diagram or so forth, and then making decisions from those arguments and inferring what's going on and coming to some conclusion with that context and stepping it up from there and giving you a chance to practice before we go on to other stuff for scientific method and designing it and so forth and analyzing, coming to the end. So as always at this point in time, I really do hope that you are doing good, and that maybe try to, at this time, do something good for yourself. Doing something good for yourself can make you feel good, and then you feel good could lead to you helping others and then helping them from there. Or maybe you can just go and help others and that makes you feel good. And even if it's the smallest thing, this can grow bigger. I don't got the data here yet, but it can grow bigger, and maybe we can make this world a better place, one little kind act at a time, even just sharing a positive story. Now, after all this, please go get some rest, and then go and review and feel good.